Look up at the night sky and you see stars, the moon, distant planets. But what you're really seeing is just the surface, the nearest streetlights of a city whose true scale is almost unimaginable. Zoom out far beyond our Milky Way, past the neighboring galaxies, and the universe reveals its true architecture, a colossal, delicate, and hauntingly beautiful structure known as the cosmic web. This is not merely a collection of galaxies scattered at random. It is the largest single thing that exists, a sprawling network of shining galaxies and invisible dark matter, connected by immense, thread-like bridges stretching across billions of light years. These are the cosmic filaments, the ghostly backbone of everything, the hidden scaffolding upon which the entire visible universe is built. They are the great, unanswered question marks written across the cosmos, structures so vast their very existence challenges the limits of our perception. What secrets do these filaments hold? What forces shape them, and what invisible laws of physics govern their evolution? For generations, astronomers peered into the depths of space and saw mostly emptiness, a dark void punctuated by islands of light. But now we know the emptiness is an illusion. The true landscape of the cosmos is this intricate web-like tapestry, and those faint, wispy filaments are not empty at all. They are conduits of unseen power, highways for matter, cradles for galaxy formation, and perhaps the very keys to understanding the ultimate fate of the universe. Within their faint glow and profound darkness lie puzzles that touch upon the nature of dark matter, the origin of cosmic structure, and the mysterious energy accelerating the expansion of everything we see. This is a frontier where our knowledge ends and pure wonder begins. This journey we're about to take is not just a list of facts, it is a voyage into the heart of 25 of the universe's most profound and enduring mysteries, all centered on these cosmic threads. We will explore why they form, what they are made of, and how they dictate the lives of galaxies, including our own. We'll confront questions that have no easy answers and dive into theories that sound more like science fiction than established science. From the nature of the dark matter flowing through these veins of the cosmos to the possibility of entire universes beyond our own cosmic web, we are about to unravel a story written on the grandest possible canvas. Prepare to have your understanding of reality challenged, your sense of scale shattered, and your curiosity ignited as we begin to pull on the threads of the cosmic web and see what unravels. So how did this magnificent cosmic architecture, this vast network stretching across the emptiness, first come to be? This brings us to our very first and perhaps most fundamental mystery, the origin of the filaments themselves. To understand the question, we have to rewind the cosmic clock all the way back to the universe's first fleeting moments. In the beginning, everything we see today, every galaxy, every star, every atom, was compressed into an unimaginably hot, dense, and nearly perfectly smooth soup of energy and fundamental particles. It was a featureless, uniform sea, yet somehow from that pristine uniformity, the seeds for this grand, structured web had to be planted. The leading theory points to two invisible architects working in concert, dark matter and a mysterious event called cosmic inflation. Think of cosmic inflation as the universe's initial explosive growth spurt. In a fraction of a second, the cosmos expanded faster than the speed of light, stretching a tiny, microscopic patch of space into something macroscopic. But this expansion wasn't perfectly even. Tiny quantum fluctuations, random ripples in the fabric of reality, were stretched to enormous sizes, creating regions that were ever so slightly denser than others. These minuscule overdensities became the blueprint for all future structure. Then entered dark matter, this mysterious, invisible substance which does not interact with light but does feel gravity, began to clump together under its own weight, drawn to those slightly denser regions laid down by inflation. Over billions of years, this dark matter formed a massive, invisible skeleton, a cosmic scaffolding. Ordinary matter, the stuff that makes up stars and planets and us, was then simply pulled along for the ride, flowing into the gravitational wells carved out by the dark matter, eventually condensing along these invisible lines to form the glowing filaments of galaxies we can now observe. Supercomputer simulations of this process are breathtaking, showing a virtual universe evolving from a smooth, cloudy haze into an intricate, web-like structure that looks almost exactly like what our telescopes reveal. Yet, for all the elegance of this theory, huge gaps in our understanding remain. We still don't know what dark matter actually is. Is it a sea of exotic particles or something even stranger? We also don't fully understand the precise physics of that inflationary period. What force could possibly cause the universe to expand so violently, and why did it stop? The transition from a smooth universe to a slightly lumpy one, and then to the specific thread-like structures we see, involves complexities that our best models still struggle to capture. Why, for instance, do filaments have the specific thickness and distribution we observe? Why didn't the universe just form into isolated, giant clumps? The precise mechanisms that sculpted the delicate filaments from the primordial chaos, determining their exact size, strength, and arrangement, remain one of cosmology's most profound and humbling unsolved problems. We see the grand cathedral, and we have a rough sketch of its foundation, but the identity of the master mason and the exact blueprints used are still hidden in the shadows of the early universe. But even if we understand the gravitational blueprint laid down by dark matter, that still leaves us with a very tangible question. What exactly are we looking at when we see one of these filaments? If we could somehow take a sample, what would it be? This leads us directly to our second great mystery, the true composition of the cosmic filaments. Our first instinct might be to point to the brilliant strings of galaxies we see in telescope surveys, but that's a cosmic illusion, like seeing the lights of a distant city at night and misting the entire city for just those pinpricks of light. The galaxies are merely the glittering ornaments hanging from the tree. They are not the tree itself. The overwhelming majority of a filament's substance is in fact completely invisible to our telescopes. The primary ingredient is the same mysterious stuff that forms the cosmic scaffolding, dark matter. This enigmatic substance, which we can only detect through its gravitational pull, makes up the massive underlying backbone of every filament. It's the unseen mountain range whose gravitational peaks guide the flow of everything else. But what about the ordinary matter, the atoms that make up you, me, and every star? Where did it all go? For decades, astronomers faced a missing baryon problem. When they added up all the normal matter they could see in stars and galaxies, it accounted for only about half of what the Big Bang theory predicted should exist. The cosmic filaments provide the answer. The space within them is not empty. It is filled with an incredibly diffuse, superheated soup of protons and electrons known as the warm-hot intergalactic medium, or WIM. The name itself is wonderfully descriptive. It's warm by astronomical standards, reaching temperatures of hundreds of thousands to millions of degrees, and it's hot enough to be in a plasma state, where atoms are torn apart into their constituent particles. This tenuous gas is so thin that a single coffee mug full of it would contain only a handful of particles, a vacuum far more extreme than anything we can create in laboratories on Earth. Yet, because these filaments are so immensely long and vast, the WIM collectively accounts for nearly all of the universe's missing ordinary matter. It is the hidden ocean in which all galaxies swim. The profound challenge and the core of this mystery is that this primary component of the cosmic web is almost undetectable. The WIM is too hot to glow in visible light and too thin to emit strong, concentrated radio waves. So how do we know it's there? Astronomers have become cosmic detectives, using indirect methods to catch glimpses of this ghostly material. One technique is to look for its faint, telltale X-ray emission. At millions of degrees, the gas in the WIM should glow softly in high-energy X-rays. Our most powerful X-ray observatories, like Chandra and XMM Newton, are now sensitive enough to have detected this faint, diffuse glow emanating from the spaces between galaxies in massive galaxy clusters, providing our first direct evidence of this hot, intergalactic reservoir. Another, even more clever method involves using the universe's natural backlights, distant, brilliant objects known as quasars. As the light from a quasar travels billions of light years to reach us, it passes through these invisible filaments. The atoms in the WIM, even in their sparse distribution, will absorb very specific wavelengths of this light, leaving behind a unique fingerprint, a series of dark lines in the quasar spectrum. It's like analyzing the light from a distant lighthouse through a faint cosmic fog. By studying what's missing from the light, we can determine the composition and properties of the fog itself. These absorption lines have been successfully observed, confirming that the space between galaxies is indeed populated by vast amounts of this warm, ionized gas. Yet, despite these breakthroughs, the true nature and detailed structure of the WIM remain deeply mysterious. We have only detected it in the densest, hottest parts of the web, near the intersections where galaxy clusters collide. What about the longer, thinner stretches of filament which are predicted to contain the majority of this material? Our current technology struggles to see it there. Is the WIM a smooth, uniform haze, or is it a turbulent, dynamic medium with its own complex weather patterns of shock waves and flows? We simply don't know. Furthermore, the exact relationship between the invisible dark matter backbone and the ordinary matter of the WIM is still unclear. Does the gas simply trace the dark matter's distribution, or are there complex feedback processes where supernova and black holes in galaxies pump energy back into the filaments, reheating the gas and altering its flow? Unlocking the full story of the filament's composition is more than an academic exercise. It is fundamental to understanding the life cycle of matter in the universe, from its primordial origins to its eventual fate, locked away in stars or drifting in these vast intergalactic reservoirs. Now, if we accept that dark matter provides the invisible framework, the gravitational blueprint for the entire cosmic web, we are immediately confronted by a staggering reality. The universe's largest structures are shaped by something we cannot see, touch, or even fully define. This brings us to our third and perhaps most humbling mystery, the role of dark matter itself. We speak of it as the primary architect, but what does that mean in practice, and how can something so fundamental remain so utterly elusive? Picture this process not as a gentle pulling, but as a relentless cosmic sorting. In the early universe, dark matter, unaffected by the intense radiation pressure that buffeted ordinary matter, was free to begin collapsing under its own gravity far sooner. It formed an extensive, invisible network of tendrils and knots, a vast three-dimensional spiderweb of gravitational potential. Think of it as a network of deep, wide river valleys carved into the very fabric of space-time. Then, as the universe expanded and cooled, ordinary matter, the atomic stuff we're made of, simply flowed into these pre-existing valleys. The dark matter didn't push or pull the atoms directly. It simply shaped the landscape, and the atoms followed the path of least resistance, eventually pooling and condensing to form the galaxies we see strung along the filaments like pearls on a string. Without this dark matter skeleton, the universe would be a vastly different and much more boring place, a sparse, nearly uniform haze of gas with no grand structures, no galaxies, and likely no us. The cosmic web is in essence a monument to dark matter's invisible hand. Yet here lies the central paradox. We can map the profound influence of this substance with incredible precision, but its fundamental nature remains one of the greatest unsolved puzzles in all of physics. What is it actually made of? For decades, the leading candidates have been WIMP, or weakly interacting massive particles. These are hypothetical particles that are heavy by subatomic standards, and as their name implies, interact with ordinary matter only through the weak nuclear force and gravity. The hope was that we might detect them indirectly by observing their mutual annihilations in space, or directly by building exquisitely sensitive detectors shielded from cosmic rays deep underground. In labs buried under mountains or in old mines, scientists wait for the once-in-a-lifetime event where a WIMP might bump into the nucleus of an atom in a vat of ultra-pure liquid, sending a tiny, measurable tremor through the apparatus. But despite decades of searching with ever more sensitive experiments, these WIMP have stubbornly refused to show themselves. This lack of detection has fueled interest in another compelling candidate, the Action. In stark contrast to the heavyweight WIMP, the Action is theorized to be incredibly light, potentially trillions of times lighter than an electron. It was originally proposed to solve a completely different, esoteric problem in particle physics concerning the symmetry of nuclear forces. If actions exist, they will be produced in vast numbers in the early universe and could collectively behave as a cold, wave-like fluid that clumps together under gravity. Their detection requires a completely different approach, using powerful magnetic fields to potentially convert these ghostly particles into faint microwave photons. Experiments are now underway to hunt for this telltale signal. Beyond these two front-runners, other, even more exotic ideas are on the table. Could dark matter be made of primordial black holes, forged in the first chaotic second after the Big Bang? Or could it be part of a hidden sector of particles that barely talk to our own familiar reality? The quest to identify dark matter is not merely an academic exercise. It is a direct investigation into the architecture of reality. The specific properties of the dark matter particle, its mass, how it interacts with itself, and even its temperature dictate the very shape and texture of the cosmic web we observe. For instance, if dark matter were warm, meaning its particles were lighter and faster moving, it would have smoothed out the smallest scale structures in the universe, potentially preventing the formation of the very thinnest filaments and the smallest dwarf galaxies. Our detailed maps of the cosmic web, therefore, act as a colossal laboratory, constraining what dark matter can and cannot be. Every thread of the cosmic web, every glittering galaxy within it, is a data point in this grand experiment. We are caught in a fascinating loop. We use the large-scale structure of the universe to infer the properties of dark matter, and we use proposed properties of dark matter to try and explain the precise details of that same large-scale structure. Until we finally catch a direct glimpse of a dark matter particle, either in a lab on Earth or through an unambiguous signal from space, the true identity of the universe's master architect will remain just beyond our grasp, its presence felt everywhere but its face forever hidden in darkness. So we've seen how dark matter forms the invisible framework and how the ordinary matter, the stuff we're made of, flows into that framework to create the glowing structures we observe. But this elegant picture once contained a glaring inconsistency that troubled astronomers for decades, a cosmic accounting error that brings us to our fourth great mystery, the case of the missing baryons. In cosmology, baryons is essentially a fancy term for ordinary matter protons, neutrons, and electrons, the building blocks of atoms, planets, stars, and us. Based on incredibly precise measurements of the early universe, specifically the cosmic microwave background radiation, we know exactly how much of this ordinary matter was created in the Big Bang. Think of it as the universe's original inventory list, when cosmologists added up all the baryonic matter they could see in the present-day universe, all the stars in all the galaxies, all the glowing gas clouds, all the dust, they came up shockingly short. Nearly half of all the ordinary matter that should be there, that must be there, was simply unaccounted for. It was as if you carefully counted your groceries at the store, paid for them, but arrived home with half the bags missing. Where did it all go? The prime suspect for a long time was the cosmic web itself, specifically the vast, empty-looking spaces within the filaments. The theory was that the missing matter wasn't clumped into visible galaxies, but was instead spread out in an incredibly diffuse hot gas, a ghostly atmosphere filling the cosmic void. This is the warm, hot intergalactic medium, or WIM, that we touched on earlier, but suspecting a culprit and catching it red-handed are two very different things. This thin, hot gas is notoriously difficult to observe. It doesn't glow brightly in any single wavelength. It's too hot for optical telescopes and often too thin and diffuse for X-ray observatories to see clearly, except in the very densest knots of the web. For years, it remained a theoretical concept, a proposed solution without definitive proof. The breakthrough in this cosmic detective story came from an unexpected tool: fast radio bursts. These are among the most enigmatic phenomena in the universe: brief, intense flashes of radio waves that last for just milliseconds, originating from galaxies billions of light-years away. While their sources are still debated, their utility for cosmologists is undeniable. As these powerful bursts travel across the cosmos on their way to our telescopes, their radio waves pass through the very filaments of the cosmic web that we're trying to probe. The tenuous gas in the WIM, while incredibly sparse, is still populated with free-floating electrons. These electrons interact with the radio waves, causing a very slight delay in their arrival, an effect called dispersion. The more material the burst travels through, the greater the delay, especially at lower radio frequencies. It's analogous to how light bends when it passes through a glass of water. By measuring the precise amount of this dispersion delay across different frequencies, astronomers can effectively measure the total number of electrons the signal encountered on its long journey. By analyzing many fast radio bursts from different distances and directions, scientists can then work backwards to calculate the average density of matter along the line of sight. And the results have been spectacularly conclusive. The amount of diffuse, ionized gas these measurements reveal in the spaces between galaxies matches, almost perfectly, the amount of missing baryons predicted by our models of the Big Bang. The case, it seems, is closed. The missing matter wasn't missing at all. It was simply hiding in plain sight, spread so thinly across the cosmic filaments that it was almost invisible to our traditional observation methods. But this discovery, while solving one mystery, opens the door to a host of new and more intricate questions. Now that we know the WIM exists, we want to understand its properties. Is it a uniform, serene ocean, or is it a turbulent and dynamic medium, stirred by colossal shock waves from galaxy collisions and supernova explosions? How exactly does this intergalactic gas cycle into and out of galaxies, feeding their growth or being expelled by their violent activity? To answer these questions, astronomers are employing a whole suite of other tools. Quasar absorption lines remain a powerful technique, acting like a cosmic spectrophotometer. When the brilliant light of a distant quasar passes through a filament, specific elements in the WIM, like oxygen, neon, and carbon, absorb very particular wavelengths of that light. By analyzing the resulting dark lines in the quasar's spectrum, we can determine not just the presence of the gas, but its temperature, density, chemical composition, and even its velocity. It tells us the weather inside the filament. Furthermore, the next generation of X-ray telescopes, with vastly improved sensitivity, are being designed specifically to map the faint X-ray glow of this gas in finer detail than ever before, hoping to trace the full extent of these filamentary rivers of matter, not just at their dense intersections, but along their entire incredible length. So the story of the missing baryons is a testament to scientific ingenuity. It shows how a persistent puzzle, when attacked with creative thinking and new technological tools, can transform from a confusing anomaly into a cornerstone of our understanding, revealing a universe where even the emptiest-looking spaces are, in fact, teeming with hidden activity. Grasping the sheer size of the cosmic web's filaments is a challenge that pushes human imagination to its absolute limit. We can talk about numbers, distances of hundreds of millions of light years, but our minds simply aren't wired to comprehend what that truly means. To put it in perspective, consider our own Milky Way galaxy, a vast island of hundreds of billions of stars. It's about 100,000 light years across. Now imagine a single cosmic filament, a thread so immense that it could have thousands of galaxies like our own strung along its length, and that thread itself could be 5,000 times longer than our entire galaxy is wide. These are not mere structures, they are the superhighways of the cosmos, the grand connectors linking the most massive concentrations of matter in the universe, the galaxy clusters. A single one of these filaments can form a bridge between clusters, meaning the distance from one end to the other can encompass a volume of space so vast it defies all earthly analogy. To make this a little more tangible, try this mental image. Picture a delicate, dew-covered spider web you might see on a morning walk. Now, imagine scaling that web up until it was large enough to envelop our entire planet. On that planetary scale, the individual threads of the web would still be incredibly thin and faint, but their total length would be almost incomprehensible, wrapping around the globe in an intricate, sprawling pattern. Now take that same concept and apply it to the observable universe. The filaments of the cosmic web are those threads, and the galaxy clusters are the dense, glittering knots where the threads intersect. The true marvel is that this cosmic spiderweb is not draped around the universe. It is the large-scale structure of the universe itself. We are living inside it. Mapping the full, uninterrupted extent of even a single one of these cosmic bridges is one of the most formidable tasks in modern astronomy. The primary obstacle is a simple, brutal fact of nature. These structures are incredibly faint and exist at staggering distances. When we look at a filament, we are not seeing a solid, glowing rod. We are seeing a sparse collection of galaxies, and with immense difficulty, the faint glow of the hot gas between them. Much of the filament's mass is the invisible dark matter, which emits no light at all. To trace a filament from one end to the other, astronomers must perform a kind of cosmic connect the dots, using sophisticated computer algorithms to analyze the three-dimensional positions of millions of galaxies to see which ones are gravitationally linked into these long, linear chains. This is like trying to trace the outline of a continent from a satellite photo by only looking at the lights of its major cities, while the actual landmass remains shrouded in darkness. The faintness of the gas within the filaments presents another layer of challenge. The warm, hot intergalactic medium is so diffuse that its light emission is drowned out by brighter foreground sources, including the glow of our own atmosphere and the scattered light from our solar system. It's like trying to spot a single, dim candle flame from miles away while standing in the middle of a brightly lit city at night. Our telescopes, even the most powerful ones in space, have to stare at a single patch of sky for days, even weeks, to collect enough photons to reveal the faintest whisper of this intergalactic material. And because these filaments are so long, creating a complete map of just one requires piecing together observations from multiple telescopes and surveys, a painstaking process that is like assembling a mosaic of a giant's portrait where most of the tiles are nearly transparent. This monumental effort is not just for the sake of creating a pretty map, it is crucial science. The specific lengths, thicknesses, and connectivity of the filaments are a direct imprint of the physics of the early universe and the properties of dark matter. By measuring their true scale, we are effectively taking the universe's vital signs, testing our most fundamental theories of how everything came to be. Every new, faint strand we manage to trace across the void is another piece of the puzzle, helping us understand the skeleton of the cosmos we call home. But as we trace the faint, immense rivers of gas that define the cosmic filaments, we encounter a force that seems almost out of place in the vast emptiness: magnetism. This brings us to our sixth profound mystery, the enigma of cosmic magnetic fields. We typically think of magnets as things we stick to our fridge or the force that guides a compass needle. It feels local, terrestrial, yet incredibly, astronomers have detected the faint but distinct imprint of magnetic fields woven through the fabric of some cosmic filaments. This discovery is as startling as finding a familiar street sign in the deepest, most uncharted wilderness. How can such organized magnetic force exist in the near-perfect vacuum of intergalactic space, and what cosmic generator could possibly be powerful enough to create it? The puzzle begins with the question of origin. There are two leading and dramatically different theories for where these fields came from. The first is a primordial origin, suggesting that magnetic fields were born in the universe's fiery infancy. In this scenario, tiny magnetic seeds were generated during the violent turbulence of the Big Bang or the subsequent period of inflation. These initial fields would have been unimaginably weak and chaotic, but as the universe expanded and matter began to coalesce into the cosmic web, these magnetic seeds were stretched and amplified alongside the gas and dark matter. Think of it like pulling on a tangled ball of magnetic string. As space itself stretched, the fields within it were drawn out, becoming larger and more organized, eventually aligning with the immense filamentary structures. If this is true, then these magnetic fields are ancient fossils carrying information about the universe's most extreme initial conditions. The second theory places the blame or the credit on the bustling activity of galaxies themselves. Throughout their lives, galaxies are incredibly dynamic. Supernova explosions, powerful jets erupting from supermassive black holes, and galactic winds constantly eject magnetized material out into intergalactic space. This isn't a gentle seepage, it's a violent expulsion. As this magnetized plasma from many different galaxies flows into a filament, it could tangle, merge, and be stretched by the vast flows of gas within the filament itself, effectively polluting the intergalactic medium with magnetic fields. In this view, the filaments are not born with magnetism, they inherit it from the busy galactic cities they connect. It's the difference between a forest that grew from seeds scattered by a primordial storm versus one that was planted by generations of settlers living on its edge. Determining which of these stories is correct, or if both are at play, is a major focus of current research, as the answer would tell us if magnetism is a fundamental property of space-time itself, or a later byproduct of cosmic evolution. Regardless of how they got there, the presence of these magnetic fields is far from a passive curiosity. They play an active and crucial role in shaping the cosmic environment. One of their most important functions is channeling and accelerating cosmic rays. These are not rays of light, but high-energy subatomic particles, mostly protons and electrons, racing through space at nearly the speed of light. Cosmic rays are notoriously difficult to pin down, as magnetic fields bend their paths, turning them into a confusing haze. But the magnetic fields within filaments can act as immense intergalactic particle accelerators and guiding conduits. They can trap these high-energy particles, forcing them to travel along the filament's length like cars confined to a cosmic freeway, preventing them from scattering randomly into the empty voids. This means the filaments could be the primary transport system for some of the universe's most energetic particles, funneling energy from one galaxy cluster to another. Furthermore, these magnetic fields directly influence the behavior of the gas itself, the very lifeblood of the cosmic web. Even a weak magnetic field can impart a tension that resists turbulence and affects how the gas collapses to form new galaxies. In the hot, diffuse plasma of the warm, hot intergalactic medium, magnetic fields can suppress the formation of small-scale clumps, regulate the flow of heat, and even help shape the stunning, ribbon-like structures we observe. They are the unseen puppet masters, subtly directing the flow and fate of the material that will one day become new stars and planets. The great frustration, however, is that detecting and measuring these fields is monumentally difficult. Their signals are incredibly faint, often buried in the noise of other cosmic emissions. Astronomers must use indirect methods, such as studying the polarization of radio waves from background sources, or looking for the faint synchrotron radiation emitted by electrons spiraling around the magnetic field lines. Each new observation is like trying to listen for a whisper in a hurricane. The strength, the structure, and the precise influence of magnetism on the grandest of cosmic scales remain one of the most elusive and captivating frontiers in our quest to understand the architecture of everything. All those glittering galaxies strung along the cosmic filaments might appear serene and fixed in place, but that is a cosmic illusion. The universe is in constant dynamic motion, and the cosmic web is its grandest transit system. This brings us to our seventh mystery, the relentless flow of galaxies. Far from being stationary, entire galaxies are caught in a slow, majestic river, streaming along these filamentary highways, pulled inexorably toward the dense, crowded intersections where massive galaxy clusters reside. If you could speed up time, you would see the universe not as a static map, but as a living, breathing entity with galaxies sliding along invisible tracks like commuters on a cosmic subway, all heading downtown to the most massive gravitational hubs. So what is the engine behind this immense, coordinated movement? The dominant force is without a doubt gravity. The invisible scaffolding of dark matter creates a landscape of hills and valleys in space-time, and galaxies, being relatively small in this grand scheme, simply roll downhill. The immense concentration of mass in a galaxy cluster at the end of a filament creates a profound gravitational trough, a cosmic slope that everything in the vicinity naturally slides down. Think of it like a vast, gentle watershed on a continental scale. Rain that falls across a mountain range eventually flows into streams, then rivers, all converging toward the ocean. In the cosmic web, galaxies are like droplets in this watershed, and the filaments are the rivers guiding them toward the gravitational ocean of a galaxy cluster. This flow isn't a sudden, violent plunge. It's a gradual, accelerating drift that plays out over billions of years. A slow-motion migration dictated by the universe's most fundamental force. However, the story might not be as simple as gravity alone. Astronomers are beginning to question if other, more subtle forces are also shaping this journey. One compelling idea involves the very gas that permeates the filaments, the warm, hot intergalactic medium. As a galaxy moves through this tenuous but present medium, it could experience a form of cosmic friction or pressure. While the gas is incredibly diffuse, the speeds involved are immense, and over millions of light-years of travel, even a slight drag could influence a galaxy's speed and trajectory. Furthermore, the chaotic energy within the filaments themselves might play a role. Colossal shock waves generated by earlier galaxy collisions or by the violent activity of supermassive black holes can ripple through the intergalactic gas. These shocks could act like cosmic tailwinds or headwinds, either giving a galaxy an extra push or creating pockets of higher pressure that slow it down. It's the difference between a boat drifting down a calm, smooth river versus one navigating a waterway with constant undertows, whirlpools, and sudden currents. The consequences of this galactic flow are profound and directly shape the universe we see today. For a galaxy, the journey along the filament is a transformative experience. As it streams toward the cluster, it may encounter other galaxies, leading to gentle interactions or even dramatic mergers that trigger bursts of new star formation, lighting up the galactic highway. But the final destination, the galaxy cluster itself, is often a brutal environment. When a galaxy finally arrives at the cluster's core, it plunges into an extreme density of galaxies and a much thicker, hotter soup of intracluster gas. This is where the flow often meets a violent end. A process called ram pressure stripping can occur where the pressure of the cluster's gas acts like a powerful wind, violently tearing away the galaxy's own cool gas reservoir, the very fuel it needs to form new stars. This effectively strangles the galaxy, transforming a vibrant, star-forming spiral into a quiet, red and dead elliptical galaxy. The flow along the filament, therefore, is not just a journey through space. It's a life cycle, a process of birth, interaction, and eventual quenching that determines the ultimate fate of billions of stars. Observing this flow directly is a monumental challenge, as the motions are imperceptibly slow from our vantage point. Astronomers don't see the movement itself. They infer it by meticulously measuring the redshifts of thousands of galaxies within a filament. By analyzing the tiny Doppler shifts in their light, they can map their velocities, revealing which are moving toward the cluster and at what speed. These observations have confirmed the general picture of inflow, but they have also revealed puzzling complexities. Some galaxies seem to be moving faster or slower than the pure gravity model predicts. Others appear to be moving in slightly skewed directions, as if being nudged by unseen forces. These anomalies are the clues that the full story of the cosmic conveyor belt is not yet written. Unraveling the precise balance between the relentless pull of dark matter and the more subtle hydrodynamic forces at play is key to understanding not just how galaxies move, but how the entire cosmic web evolves over time, shaping the large-scale structure of the universe from the past into the far future. Peering back in time to the universe's infancy, we confront a pivotal mystery that ties the grand cosmic web directly to our own origins. How did the very first galaxies spark to life? The current leading theory paints a compelling picture where the cosmic filaments served as more than just passive scaffolding. They acted as cosmic delivery systems and gravitational catalysts. In the early universe, the first delicate threads of dark matter began to form, creating a network of subtle gravitational channels. Ordinary matter, still a hot, diffuse fog of hydrogen and helium gas, was funneled into these streams. But the real magic happened at the intersections, the nodes where multiple filaments crossed. There, the gentle flows from different directions collided, piling up gas into deep, concentrated reservoirs of primeval material. These nodes became the universe's first gravitational wells, the designated construction sites where the density of matter finally became high enough for gravity to overcome the gas's internal pressure and thermal energy, triggering a catastrophic collapse. It was within these special, web-fed nurseries that the first protogalaxies were born. The process, however, was far from simple. For a galaxy to form, the primordial gas needed to cool down. Hot gas is energetic and resists collapse, but cooler gas can condense more readily. In the earliest stages, the only efficient coolant was molecular hydrogen, a fragile molecule that forms when two hydrogen atoms bond. The formation of this molecular hydrogen was critically dependent on the environment within the filaments. The slight density enhancements in the filaments provided just enough shielding from the intense background radiation that filled the young universe, allowing these first molecules to form and begin their crucial work of radiating heat away. As the gas cooled, it could sink further into the center of the dark matter halos at the filament nodes, creating the dense, spinning disks that would become the seeds of the first stars and stellar clusters. This intricate dance between dark matter's gravitational architecture and the complex cooling physics of ordinary gas is what ultimately allowed the darkness of the early universe to be pierced by the first brilliant points of starlight. The profound mystery that remains is the precise sequence of events. Did galaxies form first at the nodes and then grow by accreting gas steadily from the feeding filaments? Or did smaller, star-forming clumps condense all along the lengths of the filaments first, later migrating and merging to build up the larger galaxies at the intersections? The how and when of these first stars, known as population 3 stars, is a major unsolved puzzle. Theoretical models suggest these pioneers were behemoths, hundreds of times more massive than our Sun, burning ferociously bright and dying young in spectacular supernova that forever changed the chemical composition of the cosmos, seeding it with the first heavy elements. But we have yet to directly observe one. This is where our most powerful new window on the early universe comes into play, the James Webb Space Telescope. JWST is in many ways a time machine designed specifically to answer these questions. Its immense infrared sensitivity allows it to peer back to that epoch of first light, looking for the faint, redshifted glow of those infant galaxies and their earliest stars. Astronomers are using it to survey the ancient cosmos, not just to find isolated galaxies, but to map their positions in 3 dimensions, searching for the telltale signs that they are aligned along the faint, underlying filamentary structure predicted by theory. The goal is to catch the cosmic web in the act of assembly, to see the rivers of gas feeding the growing galaxies, and to witness the moment when the universe transitioned from a dark, formless void into a structured, illuminated tapestry. Every new deep-field image from JWST is scrutinized for hints of elongated galaxy distributions and over-dense nodes that could be the birthplaces of the first galactic structures. Finding this direct evidence would be a monumental step, bridging the gap between the smooth early universe and the complex cosmic web we inhabit today, finally revealing the detailed story of how our galactic ancestors were built within the universe's largest framework. But as we chart the birth and growth of this magnificent cosmic architecture, we are inevitably drawn to a question of truly epic proportions. What becomes of the web in the end? The universe is not a static painting, it is a dynamic, evolving system, and the forces that govern its future are locked in a titanic struggle. On one side, we have gravity, the great builder, the force that pulled matter together to weave the web in the first place. Its influence is local and communal, constantly working to bind galaxies and clusters more tightly, to draw the threads of the web closer. On the other side, we have a far more mysterious and lonelier force, dark energy. This enigmatic presence, which we can only infer through its effect of driving the universe's expansion to accelerate, acts as a cosmic repulsion, a relentless pressure that stretches the very fabric of spacetime itself. The ultimate fate of every filament, every cluster, and every galaxy hinges on the outcome of this cosmic tug-of-war. To understand the potential futures, we have to look at the scale of the battle. Within a galaxy cluster, or even along a dense, nearby filament, gravity is the undisputed champion. The mutual attraction between hundreds or thousands of galaxies is so powerful that dark energy's influence is negligible. These local structures are gravitationally bound, meaning they are essentially islands of stability in an expanding sea. They will continue to evolve with galaxies merging and gas cooling, but they will not be ripped apart by the universe's expansion. The cosmic web in these dense regions will hold firm, but when we zoom out to the largest scales, to the vast intercluster filaments that stretch across hundreds of millions of light years, the story changes dramatically. It is across these immense distances that dark energy's power becomes dominant. As the expansion of space accelerates, these great bridges are not simply being stretched, they are being diluted. The space within the filaments themselves is expanding, causing the density of the warm, hot intergalactic medium to drop even further. Galaxies that are not tightly bound to a cluster will find the gravitational ties to their filamentary highway weakening, the gentle pull between them slowly being overwhelmed by the increasing void stretching between them. Theoretical models paint a haunting picture of the far future. Billions of years from now, the observable universe will be a much darker and lonelier place. The galaxies within the bound clusters will have long since merged into giant elliptical galaxies, their star-forming fuel exhausted, their stellar populations aging and dimming. But outside these isolated island universes, the landscape will be desolate. The magnificent spiderweb-like structure we see today will have faded. The long, delicate filaments will have been stretched so thin that they effectively dissolve. The galaxies that once traced their paths will have receded so far from one another that their gravitational connection is severed. From our perspective, any civilization existing within a bound cluster would look out into a profound and ever-deepening blackness. The other clusters, once connected by luminous threads, would have vanished over the cosmic horizon, their light stretched beyond detectability and their gravitational influence completely severed. The cosmic web would become a ghost, its memory preserved only in the tightly bound relics of its densest nodes. This leads to a truly mind-bending possibility known as the Big Rip scenario, a more extreme version of this dark energy-dominated fate. In this model, the strength of dark energy is not constant but increases over time. If that were to happen, the acceleration would not just continue but would intensify. First, the intercluster filaments would be torn apart. Then, as the repulsive force grew stronger, it would begin to overwhelm even the gravity-holding galaxy clusters themselves together. Galaxies would be flung apart. Later, the gravitational glue of individual galaxies would fail, stars scattering into the void. In the final, terrifying moments, even planetary systems, stars, planets, and eventually atoms and atomic nuclei themselves would be ripped apart by the uncontrollable expansion of space. While most current data suggests this ultimate catastrophe is unlikely, the mere fact that it is a plausible theoretical outcome based on our current incomplete understanding of dark energy highlights just how high the stakes are. The destiny of the cosmic web is not merely an academic curiosity. It is a proxy for understanding the fundamental nature of reality and the forces that will dictate the final state of all existence. By mapping the web today and measuring how its expansion is changing over time, we are essentially reading the cosmological will of the universe, trying to decipher whether our magnificent cosmic home is destined for a quiet, cold isolation or a far more violent and final dissolution. Yet, even as we map the grand rivers of galactic flow within our observable universe, astronomers have stumbled upon a motion so strange and far-reaching that it seems to challenge our very definition of the cosmos. This is the enigma of the dark flow, a mysterious, coordinated drift on a scale that defies conventional explanation. Imagine you're in a vast, gentle river, and you can see all the other boats and debris around you moving with the current. This is the expected flow of galaxies toward the dense clusters of the cosmic web, all driven by the gravitational landscape we can map. But then you notice something unsettling. A huge collection of distant galaxy clusters scattered across billions of light years all appear to be moving slowly but steadily in the same specific direction, as if the entire river itself is sliding sideways. This isn't a flow toward any visible mass within our universe. It's a uniform drift toward a point on the cosmic horizon for which we have no obvious explanation. The evidence for this perplexing motion comes from a meticulous study of the cosmic microwave background, the afterglow of the Big Bang. This radiation fills the entire universe and provides a stationary backdrop, a fixed frame of reference against which all other motions can be measured. As galaxy clusters move through space, the hot gas trapped within them interacts with this background radiation in a subtle way, through a phenomenon known as the kinematic Sunyaev-Zeldovich effect. In simple terms, the motion of a cluster imprints a tiny, specific temperature shift on the microwave background in the cluster's direction. When scientists analyzed data from hundreds of distant clusters, they found a startling pattern. A significant number of them showed a velocity component that was aligned, all pointing toward the same patch of the cosmos. This wasn't a small, localized current. It was a bulk flow, a concerted movement of immense structures on a scale of over 3 billion light-years, far larger than any known gravitational attractor like the Shapley supercluster should be able to produce. The sheer scale of this coordinated motion suggests the gravitational source pulling them must lie impossibly far away, far beyond the edge of what we consider our observable universe. This discovery, of course, is shrouded in intense controversy. The primary point of debate is whether the signal is real or an artifact of incomplete data or unaccounted for systematic errors. Critics argue that the measured effect is at the very limits of our detection capabilities, and that other, more conventional explanations, such as an uneven distribution of mass on the largest scales that we simply haven't mapped yet, could be responsible. They point to newer data sets that have failed to reproduce the effect with the same strength. suggesting the initial findings might have been influenced by a statistical fluke or a subtle bias in the observation method. The astronomy community remains sharply divided, with some dismissing dark flow as a compelling phantom and others believing it is a groundbreaking clue to physics beyond our current horizon. For those who take the observations at face value, the implications are staggering. The most radical explanation is that the dark flow is caused by the gravitational influence of something truly unimaginable, a massive structure residing in a region of space-time that is causally disconnected from our own. Since the Big Bang, light has only had about 13.8 billion years to travel, meaning we can only see a finite volume of the universe, our observable bubble. But the entire cosmos is likely much, much larger, possibly infinite. If there is an immense concentration of mass, another supercluster, or a vast, exotic region of dense matter just outside our observable bubble, its gravitational pull could, in theory, reach across the void and tug on the matter within our own cosmic web. Gravity, unlike light, may not be bound by the same speed of light limit in its effect on the fabric of space-time, according to some cosmological models. This means we could be feeling the ghostly tug of a neighboring universe or a vastly different part of our own, whose light will never reach us, making its presence known only by setting our entire local cosmos adrift in a direction we cannot fully explain. The search for corroborating evidence is now a race of technology and theory. The next generation of space observatories and ground-based telescopes, with their exquisitely sensitive instruments, will scour the cosmic microwave background with even greater precision, attempting to confirm or finally lay to rest the existence of this cosmic current. If it is real, the dark flow would be our first empirical hint that our universe is just one small piece of a far grander, and perhaps even more mysterious cosmological structure. But for all their immense scale and intricate structure, the filaments of the cosmic web tell only half the story. To truly appreciate their form, we must also consider the spaces they enclose, the vast, hauntingly empty regions known as cosmic voids. If the filaments are the universe's great mountain ranges, then the voids are its oceanic abysses, immense, dark, and profoundly vacant. These are not merely gaps, they are the dominant feature of the cosmos by volume, immense bubbles of near-nothingness that can span hundreds of millions of light years. Their existence poses a deep and counterintuitive mystery. In a universe born from a nearly uniform soup of matter and energy, how did such staggeringly empty regions come to be, and why do they remain so devoid of both the galaxies we can see and the dark matter we infer? The formation of these voids is a tale of gravitational dynamics on the grandest scale. In the early universe, matter was distributed in a web of slight density fluctuations. Regions that were ever so slightly denser than average had a stronger gravitational pull, drawing in more and more matter from their surroundings over billions of years. Conversely, regions that were initially just a tiny bit less dense than average found themselves at a gravitational disadvantage. As matter flowed toward the developing filaments and nodes, it was effectively siphoned away from these underdense regions, leaving them behind like receding tidal pools in an outgoing cosmic sea. This process, known as gravitational evacuation, is the primary engine behind void formation. The voids are not static holes punched in the universe, they are actively expanding, their emptiness deepening as the surrounding filaments and walls grow denser and more defined. The surprising part, revealed by sophisticated computer simulations, is that the voids are not completely empty of dark matter. They do contain it, but its density is so exceptionally low that its gravitational pull is negligible. The dark matter itself has been cleared out, participating in the same great migration toward the dense filaments, leaving the voids as gravitational backwaters in the flowing river of the cosmos. This leads to a fascinating and unexpected property of these empty regions. They are among the fastest expanding parts of the universe. While the overall cosmos is undergoing accelerated expansion due to dark energy, the voids are local hotspots of this phenomenon. With very little matter inside them to provide a counteracting gravitational pull, the repulsive force of dark energy operates almost unopposed within their vast volumes. Think of the universe as a block of Swiss cheese, with the dense filaments and clusters forming the cheese and the voids as the holes. As the cheese ages, the holes naturally grow larger. In the cosmic analog, the voids are not just passively getting bigger because space is expanding. They are actively accelerating in their own growth, pushing the surrounding web of galaxies further apart. In a sense, the cosmic web is being stretched thin, not just from the outside in, but from the inside out, with these growing voids acting as engines of isolation. Yet, the boundaries between these expanding voids and the dense filaments are not peaceful, static borders. They are cosmic frontiers, zones of intense and violent astrophysical activity. As a void expands, it doesn't simply push against the filament like a gentle balloon. It creates colossal shock waves and vast streams of gas that slam into the filamentary walls. This interaction can trigger some of the most dramatic star formation in the universe, compressing gas clouds and igniting firestorms of new stellar birth along the filament's edge. It's a cosmic version of a surf zone, where the energetic outflow from the void crashes against the solid structure of the web, creating a turbulent and fertile region. Furthermore, galaxies that find themselves near the edge of a void can experience a peculiar fate. Astronomers have identified so-called void galaxies, isolated island universes that reside within the emptiness itself. These galaxies are often strange and pristine, less likely to have undergone mergers. They tend to be smaller, younger, and more slowly evolving than their cousins in the dense clusters, living quiet lives in the cosmic outback. Studying them offers a unique window into how galaxies evolve in the absence of the violent interactions that define life within the crowded web. The profound emptiness of the voids is therefore not a passive emptiness. It is an active and shaping force, its expansion sculpting the web, triggering creation at its edges, and providing a unique laboratory for understanding galactic life in its most isolated form. Now, as we trace the history of the cosmic web from its origins to its ultimate fate, we are drawn toward a specific, pivotal moment in cosmic history, a period of profound transformation known as the Epoch of Reionization. This was the universe's Great Awakening, the time when the pervasive, neutral fog of primordial hydrogen gas was blasted apart by the first brilliant sources of light. For hundreds of millions of years after the Big Bang, the cosmos was a dark place filled with an opaque sea of neutral hydrogen atoms. Then something happened. The first stars and galaxies ignited, flooding the universe with intense ultraviolet radiation so powerful that it stripped the electrons from the hydrogen atoms, turning them back into a transparent ionized plasma. The universe has remained transparent ever since. The colossal mystery is exactly how this happened, and growing evidence suggests the cosmic web was not just a backdrop for this event, but the very conduit that shaped it. The prevailing theory is that reionization didn't occur uniformly, like a single light switch being flipped for the entire cosmos. Instead, it likely progressed in a patchy, uneven manner. The first luminous objects did not appear randomly. They formed at the dense nodes and along the filaments of the early cosmic web. Imagine the filaments as the branches of a river delta during a spring thaw. The first light sources, like snowmelt at the headwaters, began the process. Their intense radiation would have streamed most efficiently along the paths of least resistance, the very same filamentary channels that were funneling gas to feed their growth. These corridors, already cleared of the densest gas, would have allowed radiation to travel much farther than it could through the neutral wilderness of the voids. In this scenario, the cosmic web acted as a system of fiber optic cables on a universal scale, guiding and focusing the ionizing photons, creating expanding bubbles of transparent, ionized gas that eventually overlapped and filled all of space. The web wasn't just the scaffolding for the first structures, it was the plumbing system for the radiation that permanently changed the state of the entire universe. Detecting a direct signal from this formative era is one of the holy grails of modern cosmology, and it comes in the form of a whisper from the hydrogen gas itself. Before it was fully ionized, the vast sea of neutral hydrogen emitted a faint radio signal at a specific wavelength of 21 centimeters. As the universe has expanded over billions of years, that signal has been stretched or redshifted to much longer wavelengths, now residing in the meter wave band of the radio spectrum. Theoretically, by mapping the subtle variations in this signal, we could create a three-dimensional movie of reionization in progress, watching as the first bubbles of ionized gas grew and merged, tracing their outline against the neutral background. It would be the ultimate cosmic fossil, allowing us to witness the moment the cosmic web first began to glow with structure and light. The challenge, however, is that this signal is incredibly faint, buried beneath layers of overwhelming interference. The redshifted 21 centimeter signal is about 1,000,000 times weaker than the foreground radio noise from our own galaxy and from all the other galaxies that have formed since. It's like trying to hear a single, quiet conversation in a sports stadium during the final moments of a championship game. To overcome this, astronomers are building a new generation of revolutionary radio telescopes designed not for pretty pictures, but for extreme sensitivity to these subtle, large-scale signals. Projects like the Hydrogen Epoch of Reionization Array, or HERA, in South Africa, and the upcoming Square Kilometre Array in Australia and South Africa are essentially vast fields of simple radio antennas. Their power comes from their numbers and their arrangement, using a technique called interferometry to combine the signals from thousands of antennas, effectively filtering out the localized, point-like sources of interference to isolate the faint, diffuse cosmological background. They are listening for the cosmic static of creation itself. The data from these ambitious experiments is already beginning to place constraints on our models, helping us rule out some scenarios for how quickly reionization unfolded. But the final prize, a clear, unambiguous map of the neutral hydrogen during the epoch of reionization, remains just out of reach. The technical hurdles are immense, requiring not just incredible sensitivity, but also the ability to meticulously subtract the foreground signals with near-perfect precision. A single error in calibration or an unaccounted-for source of radio frequency interference from human technology can contaminate the entire data set. The hunt for this signal is a painstaking collaborative effort that pushes the limits of our engineering and our data processing capabilities. Success would not only illuminate the role of the cosmic web in one of the universe's most dramatic transitions, but would also provide a direct look at the very first structures to ever form, revealing the moment the darkness of the cosmic dawn was permanently banished by the light of the first stars. Considering those vast, delicate filaments stretching across the cosmos, a deeply perplexing question naturally arises: how do they possibly hold themselves together? It seems almost counterintuitive. We're talking about structures that are billions of light-years long, yet only tens of millions of light-years thick. On a human scale, that's like a single strand of spider silk stretching from the Earth to the Moon and beyond, but remaining perfectly intact for billions of years. Given the relentless pull of gravity and the equally powerful stretching force of dark energy, why haven't these cosmic threads either collapsed into dense knots or simply evaporated into the expanding void? Their enduring stability is a riddle that points to a complex and delicate balancing act happening on the grandest of stages. At the heart of this puzzle is a fundamental tug of war between two opposing cosmic forces. On one side, you have gravity, the great unifier. Within each filament, the combined mass of the dark matter backbone and the diffuse, hot gas creates a self-gravitating system. This gravity is constantly working to pull the filament inward to make it contract and thicken. It's the same force that wants to clump a cloud of dust into a ball. Left unchecked, this inward pull would cause the filament to fragment, pinching off into a string of galaxy clusters like beads on a necklace, but it doesn't. This is where the internal dynamics of the filament come into play. The gas within the filament isn't stationary, it's in motion. It has pressure and temperature, and it often has a degree of turbulence stirred up by the inflow of matter from the voids and the occasional galactic explosion. This internal pressure provides an outward push that resists gravity's constant, crushing embrace, helping the filament maintain its slender form against collapse. And then, pulling in the exact opposite direction, you have dark energy. This mysterious force, which drives the accelerated expansion of the universe, is constantly trying to stretch the filament apart, to dilute its matter and sever its connections. It acts like a relentless cosmic tension, trying to pull the thread until it snaps. For the filament to survive, the inward pull of its own self-gravity must be strong enough to overcome this outward stretching on its local scale. This creates a fascinating cosmic zoning law. On the very largest scales, the immense distances between separate galaxy clusters, dark energy wins and the expansion proceeds. But within the local environment of a filament where the density of matter is high enough, gravity remains the dominant force, creating a locally bound structure that can resist being torn apart by the background expansion of space. The filament exists in a precarious equilibrium, a stable river of matter flowing through an expanding landscape, but gravity and pressure alone don't tell the whole story. The invisible component, the dark matter, plays the most crucial role of all. Think of the dark matter halo surrounding a filament as a vast, massive sheath that provides a stable gravitational trough. Ordinary gas flows into and through this pre-existing stable channel. The dark matter doesn't collide or experience friction. It simply provides a steady, unwavering gravitational potential that holds the entire structure together. It's the ditch that guides the river. Furthermore, filaments are not isolated. They are part of an interconnected web. A single filament is anchored at both ends by incredibly massive galaxy clusters. These clusters act like giant gravitational anchors, pinning the filament in place and constantly feeding it with fresh material from the surrounding voids, a process known as accretion. This continuous, if slow, inflow of matter may help to replenish the filament and stabilize it against both collapse and dissipation over cosmic time. The stability we observe, therefore, isn't a static snapshot. It's a dynamic, ongoing process, a fragile dance between contraction and expansion, between internal support and external anchors, a dance that has been continuing successfully for billions of years, weaving the enduring architecture of our visible universe. Yet, nestled within these immense rivers of gas and dark matter, another, more ghostly population of celestial objects adds to the mystery, a vast sea of stars that belong to no galaxy at all. These are the intergalactic stars, also known as rogue stars or intracluster stars, solitary suns adrift in the profound darkness between galaxies, illuminating the cosmic filaments from within like lonely lighthouses in an endless ocean. Their very existence challenges our most fundamental ideas about where and how stars can form, suggesting that the processes of stellar birth and stellar exile are far more complex and widespread than we ever imagined. To find a single star, isolated and free-floating in the intergalactic void, is to find a story of cosmic violence or of quiet, improbable creation. So how did these stellar orphans come to be? Astronomers have uncovered two primary, dramatic pathways that can strand a star in the emptiness. The first, and likely the most common, is a tale of gravitational chaos. Galaxies within the dense environments of clusters and groups are constantly interacting, swinging past one another in a dynamic cosmic dance. During a close encounter, or more dramatically, a full-scale galactic merger, the intricate gravitational fields of the colliding galaxies can act like a colossal slingshot. Stars can be ripped from their galactic moorings and flung out into intergalactic space at tremendous speeds, becoming hypervelocity stars on a one-way trip into the void. It's a stellar ejection event of almost unimaginable power. Furthermore, when galaxies merge, their central supermassive black holes eventually sink toward the center of the new combined galaxy, orbiting each other in a tight binary pair. As they spiral inward, their immense gravity can fling entire stars from the galactic core out into the great beyond, a process known as gravitational slingshotting. These stars become permanent exiles, condemned to wander the dark filaments alone. The second possibility is even more intriguing, that some of these stars were never part of a galaxy to begin with. They may have formed in situ right there in the deep solitude of the filament. While the gas within the cosmic web is incredibly diffuse, it is not completely uniform. In certain regions, particularly within the denser parts of a filament or near the turbulent boundaries of growing voids, the tenuous gas could theoretically collapse under its own gravity. This would require conditions that are just right, a slight density enhancement, perhaps aided by the shock waves from a nearby galactic collision or the gentle compression of a passing dark matter subhalo. If such a cloud of gas could cool and condense enough, it might fragment and collapse to form stars directly in intergalactic space. These would be true natives of the void, born from the sparse raw material of the cosmic web itself, never knowing the crowded confines of a galactic disk. The very idea forces us to expand our definition of a star-forming environment, pushing it into realms we once considered far too empty and serene for such a violent, energetic process. Detecting these solitary suns is a monumental challenge, as a single star at such a vast distance is an incredibly faint pinpoint of light. Astronomers don't typically spot them one by one. Instead, they detect their collective ghostly glow. In the cores of massive galaxy clusters, this diffuse light, known as the intracluster light, can be substantial. It is a faint, omnipresent luminosity that permeates the space between the galaxies, created by the combined light of billions upon billions of these rogue stars. By using extremely sensitive cameras on the world's largest telescopes and employing sophisticated image processing techniques to subtract the brilliant light of the individual galaxies, astronomers can map this faint intracluster glow. It reveals itself as a soft, ethereal haze, a testament to the vast population of stars that have been stripped from their homes over billions of years of cosmic history. In some clusters, this intracluster light accounts for a significant percentage of the total stellar mass, proving that this is not a minor phenomenon, but a major component of the universe's structure. The presence of these intergalactic stars profoundly impacts our understanding of the cosmic filaments. They contribute measurable mass to these structures, adding to the total budget of both ordinary and, through their eventual death, dark matter within the web. But perhaps more importantly, they serve as tracers. These stars are like breadcrumbs left behind from past galactic interactions. By studying their distribution, their numbers, and their motions, astronomers can reconstruct the violent history of the galaxy cluster, piecing together a timeline of which galaxies merged and when. A large population of rogue stars suggests a dynamically active and violent past where galactic collisions were frequent. A smaller, more diffuse population might indicate a quieter history. Furthermore, the chemical composition of these stars, if we can ever obtain their spectra, would be a dead giveaway of their origin. Stars born in the pristine environment of a filament, from gas that has been largely unenriched by multiple generations of supernova, would have a very different chemical fingerprint compared to stars ejected from the metal-rich cores of mature galaxies. They are, in every sense, fossil records of the construction of the cosmic web, their lonely light illuminating not just the dark spaces between galaxies, but also the dynamic processes that have shaped the universe we see today. This grand cosmic architecture, with its immense filaments and vast voids, might seem disconnected from our tiny world, But what if this largest of all structures played a direct and crucial role in our very existence? This leads us to a truly profound speculation: the cosmic web's influence on life itself. It's a staggering thought that the universe's sprawling skeleton could have set the stage for the emergence of conscious beings on a small, rocky planet. The connection lies in a concept we know well on a planetary scale: the Goldilocks zone, that just right region where conditions are neither too hot nor too cold for liquid water and life. What if galaxies and the solar systems within them have their own cosmic Goldilocks zone dictated by their specific address within the web? Our home, the Milky Way, offers a compelling case study. We do not reside in a dense, violent galaxy cluster at a bustling intersection of filaments, nor are we adrift in the sterile emptiness of a deep void. Instead, we occupy a relatively quiet suburban region, part of what's known as the local sheet, a filamentary wall of galaxies that includes our local group with Andromeda and the Triangulum galaxy. This specific location may be a primary reason we are here to ponder it. Life, particularly complex life, likely requires long periods of stable planetary evolution, free from constant sterilizing cataclysms. The dense core of a galaxy cluster is a dangerous environment, with frequent galactic collisions and close encounters that can wrench solar systems from their orbits, and where intense radiation from countless neighbors could scald any budding biospheres. Conversely, a galaxy isolated in a void might struggle to acquire enough heavy elements from galactic interactions, potentially leaving its stars and planets too metal poor to form the complex chemistry life requires. Our position within a filament, but not at its most crowded node, appears to offer a remarkable balance. The gentle gravitational flow along the local filamentary structure may have guided the Milky Way's formation and provided a steady, but not overwhelming, supply of gas to fuel star formation across billions of years, allowing for the gradual, enriched stellar populations that make rocky planets like Earth possible. Beyond this general location, the cosmic web may have provided an even more specific form of protection. Our galaxy's journey through this cosmic landscape could have strategically placed our solar system in a protective bubble. There is evidence to suggest that our entire local bubble is a region of hot, diffuse plasma, carved out by a series of ancient supernova explosions that occurred millions of years ago. These colossal explosions, which seeded our region with heavy elements, also swept the local interstellar medium clear of much of its denser gas and dust. This clearing effect might have had a dual benefit. It enriched the cloud that would form our sun and planetary system with the necessary ingredients for life, while also creating a relatively low-density environment that shields us from the full brunt of interstellar radiation and cosmic rays. In this view, the gentle gravitational currents of the local filament guided the Milky Way into a celestial safe harbor, while localized stellar activity within the galaxy then scrubbed our immediate neighborhood clean, creating a stable, enriched cradle for life. The largest and smallest scales of cosmic evolution intertwine, with the web setting the galactic stage and local stellar physics setting the planetary scene. Pushing this idea even further, some scientists speculate that the cosmic web could act as a large-scale regulator for one of the universe's most mysterious phenomena, gamma-ray bursts. These are the most powerful explosions since the Big Bang, fleeting blasts of high-energy radiation that can release more energy in seconds than our Sun will in its entire 10 billion-year lifetime. A nearby gamma-ray burst pointing directly at Earth would be an extinction-level event, capable of stripping away the ozone layer and bombarding the planet with lethal radiation. The distribution of these catastrophic events is not random. Long-duration gamma-ray bursts are associated with the collapse of massive, rapidly rotating stars in regions of active star formation, precisely the kind of environments more common in the early universe and in certain types of disturbed, gas-rich galaxies. The structure of the cosmic web, by dictating the rate and history of galaxy interactions and star formation, may inherently make some galactic environments more prone to such bursts than others. A galaxy like our own, residing in a quieter filamentary suburb with a more moderate and steady star-forming history, might statistically be a much safer place for life to arise and persist over cosmological timescales than a galaxy in a chaotic cluster core, constantly being bombarded with new gas and undergoing violent bursts of stellar birth. The web, therefore, might not only provide the material for life, but also, by its very architecture, minimize the frequency of universe-wide sterilizing events in certain privileged neighborhoods. Ultimately, this line of thinking elevates the cosmic web from a fascinating structural feature to a potential key player in the story of life. It suggests that the conditions for habitability are not just about a single star or a single planet, but are woven into the fabric of the universe's largest scale structure. The specific gravitational tides, the flow of enriched gas, and the statistical probability of catastrophic events are all influenced by a galaxy's place within the cosmic tapestry. While this remains a speculative and emerging field of study, it powerfully connects our most intimate question, why are we here, to the most immense structures in existence. Our ability to look up, map the web, and ask these questions might itself be a testament to the gentle, life-fostering properties of a cosmic filament's quiet stretch, a serene galactic suburb in a universe of both chaotic cities and empty deserts. All of this talk of flows, voids, and grand structure brings us to a modern crisis in cosmology, a disagreement so fundamental it calls into question the very rate at which the universe is expanding. This is the Hubble tension, and surprisingly, the cosmic web might lie at the heart of the mystery. The problem is stark and simple. We have two primary, incredibly precise methods for measuring the Hubble constant, which is the number that describes the present-day expansion rate of the universe. The first method looks back to the very beginning, using the cosmic microwave background as a pristine snapshot of the infant cosmos. By meticulously analyzing the tiny fluctuations in this afterglow, we can run the cosmological clock forward with our standard model of the universe and predict what the expansion rate should be today. The second method looks at the local, modern universe, using celestial landmarks like Cepheid variable stars and Type Ia supernova in relatively nearby galaxies to directly measure how fast they are receding from us. Both methods are sophisticated, both are operated by brilliant teams, and both are, in their own realms, exquisitely precise. The trouble is, they don't agree. The local measurements consistently give a higher, faster expansion rate than the prediction from the early universe. It's as if you calculated the speed of a car based on its acceleration from a stoplight, but when you actually clocked it with a radar gun a minute later, it was going significantly faster than your calculation said it should be. This isn't a small, marginal error. It's a discrepancy that has persisted and even grown with more precise data, suggesting we might be missing a crucial piece of physics. This is where the cosmic web, with its intricate tapestry of dense filaments and empty voids, enters the stage as a potential culprit. Our standard cosmological model, known as lambda CDM, assumes that on the largest scales, the universe is homogeneous and isotropic, essentially smooth and the same in every direction. This assumption of a fairly uniform universe is what allows us to make clean, straightforward calculations from the cosmic microwave background to the present day. But what if that assumption is a gross oversimplification? What if our local cosmic neighborhood, the volume of space within which we make our direct measurements of the Hubble constant, is not perfectly average? The cosmic web tells us that the universe is fundamentally lumpy. We live inside a galaxy that is part of a filament, which is part of a larger wall which borders a cosmic void. This complex geography means the gravitational field around us is not uniform. We might be residing in a region of space that has a slightly different density and gravitational pull than the cosmic average. If our local patch is underdense, a bit like a gentle hilltop in the gravitational landscape, then the expansion of space within it could be slightly faster than the universal average. The emptiness of a void exerts less gravitational pull to slow things down, allowing space to stretch more freely. Our local measurements, therefore, wouldn't be measuring the true global Hubble constant. They'd be measuring a local, inflated version of it, biased by our specific address in the cosmos. We could be like sailors trying to measure the average depth of the ocean, but doing all our soundings from the deck of a ship floating in a deep but unrepresentative underwater trench. The challenge, and the reason this is still a mystery, is proving it. Is our local universe truly unusual enough to cause such a significant discrepancy? To answer that, we need an exquisitely detailed, three-dimensional map of the cosmic web's matter distribution, both seen and unseen on an immense scale. This is not just about counting galaxies, it's about weighing the entire landscape, including the dark matter and the diffuse WIM. Astronomers are tackling this with a technique called peculiar velocity surveys. Galaxies don't just move with the Hubble flow, they also have their own individual motions, their peculiar velocities, as they fall toward the gravitational attractors of the cosmic web. By carefully measuring the distances to millions of galaxies and their redshifts, scientists can separate this peculiar motion from the overall expansion. The pattern of these peculiar velocities is a direct tracer of the underlying gravitational field, revealing the hills and valleys of the cosmic landscape. If we find that galaxies in our vicinity, including the Milky Way, are all streaming away from a particularly large, nearby void, that would be strong evidence that we are in an underdense region, and that our local Hubble measurement is indeed biased. Current maps, like those from the Cosmic Flows project, do suggest we are inside a modest underdensity known as the local void, but the debate rages over whether this void is large and deep enough to account for the full magnitude of the Hubble tension. The implications of this idea are profound. If the cosmic web structure is indeed tricking our local measurements, then there is no crisis in fundamental physics. We wouldn't need to invent new types of dark energy or exotic particles. We would simply need to acknowledge that our local viewpoint is provincially biased and that our standard model of cosmology is still correct. The Hubble tension would dissolve into a cosmic cartography problem. However, if future, more detailed maps of the web show that our local environment is, in fact, quite average, then the tension snaps back with a vengeance, forcing us to consider that our understanding of the universe's ingredients or the laws of gravity themselves might be incomplete. The resolution of this mystery, therefore, hinges on our ability to see the universe not as a smooth, idealized sphere, but in all its structured, filamentary glory. The next generation of astronomical surveys, like those from the Vera C, Rubin Observatory and the Euclid Space Telescope, are designed to do exactly that, to map billions of galaxies and trace the dark matter with unprecedented precision. They will measure the cosmic web in such detail that we will finally know if we live in a special, faster expanding bubble, or if the universe is genuinely trying to tell us something new and unexpected about its ultimate fate. Stepping back from the grand structure we see today, we can trace a thread all the way back to the universe's very first fraction of a second, to a mystery that connects the cosmic web directly to the birth of spacetime itself. This is the search for the whispers of primordial gravitational waves. To understand this connection, we have to revisit the event that likely planted the very first seeds of the cosmic web, cosmic inflation. This was a period of unimaginably rapid expansion, when the universe blew up in size by a factor of trillions upon trillions in less than a blink of an eye. During this violent, explosive growth, the fabric of spacetime wasn't just stretching smoothly. It was undergoing a turbulent quantum frenzy. At these incredible energy scales, the distinction between the force of gravity and the other fundamental forces blurs, and gravity itself is thought to have become a quantum entity fluctuating wildly. According to Einstein's general theory of relativity, any accelerating mass or energy should produce ripples in the fabric of spacetime gravitational waves. We've already detected these waves from dramatic events like the mergers of black holes and neutron stars. But the theory suggests that the most colossal accelerator of all, the inflationary expansion of the entire universe, should have generated its own signature brand of gravitational waves. These wouldn't be the brief chirps from stellar collisions. They would be a persistent, universe-filling hum, a background sea of ripples with wavelengths that could stretch across the entire cosmos. These are the primordial gravitational waves, and they are hypothesized to have been generated in that first fleeting moment, their imprint frozen into the universe as it inflated. The profound link to the cosmic web is this: these space-time ripples would have carried energy, and energy, as Einstein taught us, creates gravity. The tiny fluctuations in the gravitational wave background would have directly translated into minuscule variations in the density of the universe. They would have provided the initial push, the first gentle nudge that started the process of clumping, providing the gravitational seeds that dark matter and ordinary matter would later flock to, eventually growing over billions of years into the vast network of filaments and voids. In this view, the cosmic web is the ultimate echo of a quantum gravitational storm that raged at the beginning of time. The holy grail for cosmologists is to find direct, observational evidence of these primordial waves. The most promising method involves scouring the cosmic microwave background, the afterglow of the Big Bang. The theory predicts that as these primordial gravitational waves washed through the hot, dense plasma of the early universe, they would have influenced the polarization of the ancient light. Light waves can vibrate in different directions, and gravitational waves would have imparted a very specific curl-like pattern onto this vibration, known as B-mode polarization. Finding this distinct swirl in the polarization of the cosmic microwave background would be tantamount to discovering the fossilized ripples from the universe's birth, a direct snapshot of gravity when it was still a quantum force. It would be the smoking gun that connects the largest structure we see, the cosmic web, directly to the smallest scale physics of quantum gravity. The hunt for this signal, however, is arguably the most difficult and controversial in modern cosmology. The challenge is that the expected signal is incredibly faint, and it can be mimicked or completely obscured by other astrophysical foregrounds. Interstellar dust within our own Milky Way galaxy, for instance, can also polarize light and create patterns that look frustratingly similar to the primordial B-modes we're desperate to find. This is precisely what led to a famous and dramatic moment in astronomy. In 2014, a team using a telescope at the South Pole known as BICEP 2 announced they had detected this primordial B-mode signal. The announcement sent shockwaves through the scientific community, promising a window into the physics of inflation. However, subsequent joint analysis with data from the Planck Space Telescope revealed that the signal they had seen was almost entirely due to galactic dust. The primordial signal, if it was there at all, was buried deep beneath this cosmic pollution. This episode highlights the monumental difficulty of the task, requiring not just incredibly sensitive telescopes, but also an exquisitely detailed understanding of every other source of polarization in the sky. Despite this setback, the search is far from over. New and more advanced experiments are being built and deployed, each one more sensitive and better at filtering out dust contamination than the last. Telescopes like the Simons Observatory and the planned LightBird space mission are designed to survey the sky with unprecedented precision, hoping to finally tease out the faint whisper of the universe's first tremors. A confirmed detection would do more than just explain the origin of the cosmic web. It would open a direct window into an energy regime 1 trillion times more powerful than anything we can create in particle colliders. It would tell us about the physics of inflation itself, potentially revealing what field or force drove that explosive expansion, and allowing us to test theories of quantum gravity for the very first time. The cosmic filaments, therefore, are not just a beautiful structure, they are a cosmic message in a bottle, and the primordial gravitational waves are the faint, encoded language in which that message was first written, a language we are only just beginning to learn how to read. Yet another cosmic puzzle emerges when our telescopes catch the faintest of glimmers, revealing a strange and ghostly class of objects that defy everything we thought we knew about how galaxies live and die. These are the ultra-diffuse galaxies, or UDG, and their existence is a profound mystery woven directly into the fabric of the cosmic web. Imagine a galaxy the size of our own Milky Way, with its sprawling spiral arms spanning 100,000 light-years. Now imagine that this colossal structure contains only 1% of the Milky Way stars, making it so ethereally faint that its total glow is often outshone by a single bright star within our own galaxy. That is the essence of an ultra-diffuse galaxy, a cosmic ghost, a vast, sprawling metropolis of darkness punctuated by only a few scattered streetlights. Their discovery in large numbers, particularly within and around the filaments connecting massive galaxy clusters, has sent astronomers back to the drawing board, forcing them to reconsider the fundamental recipes for building a galaxy. The central enigma is simple yet baffling. How did something so large manage to form so few stars? In our standard model of galaxy formation, a vast, extended disk of stars implies a deep and massive gravitational well, one that should have pulled in enormous amounts of gas, leading to a prolific burst of star formation that would have lit up the galaxy like a beacon. But ultra-diffuse galaxies clearly took a different path. One leading theory suggests they are failed galaxies. Perhaps they formed within dark matter halos that were, for some reason, unusually spread out, lacking the dense, central core needed to efficiently funnel gas into a compact star-forming frenzy. Alternatively, they might have been born with a standard amount of gas, but their star formation was strangled at birth. Internal dynamics, such as a high rate of spin that prevented the gas from settling, or early, gentle feedback from the first supernova, could have blown out much of their star-forming fuel before it could collapse, leaving behind a vast, dark matter skeleton with only a sparse sprinkling of stars. The plot thickens significantly when we consider their habitat. Ultra-diffuse galaxies are not scattered randomly throughout the cosmos. They show a distinct preference for the cosmic filaments. This spatial connection is a critical clue. A galaxy adrift in the deep, empty void has a quiet, isolated life, free from the gravitational harassment of neighbors. But a galaxy within a filament is subject to a constant, if gentle, tidal force, the subtle stretching pull of gravity from the massive structure it is part of. This tidal force could be the key to the ghostly nature of UDGs. As a proto-ultra-diffuse galaxy traveled along a filament toward a cluster, the relentless tidal tug might have continually puffed it up, stretching its stars and dark matter into a more diffuse configuration, effectively preventing it from ever condensing into a classic compact spiral. It's a form of cosmic yoga where the galaxy is constantly being pulled and stretched, maintaining its vast, ethereal form over billions of years. Beyond simple stretching, the environment of a filament might also act as a galactic pressure cooker, but one that prevents cooking. The tenuous but present gas within the filament, the warm, hot intergalactic medium, could exert a constant low-level pressure on a galaxy moving through it. For a massive galaxy like the Milky Way, this ram pressure is negligible. But for a smaller, less massive galaxy with a weaker gravitational grip, this persistent pressure could slowly but steadily strip away its outer reservoirs of gas, starving it of the fresh fuel needed for future star formation. This process would be far more gentle and prolonged than the violent stripping that occurs in cluster cores, allowing the galaxy to retain its existing stars while ensuring no new ones are born, leaving it to slowly fade into a permanent diffuse state. The filament in this scenario is not just a passive highway, but an active participant in shaping the bizarre properties of the galaxies that journey along it. The mystery deepens even further with the discovery that some ultra-diffuse galaxies are not just faint, but also anomalously rich in dark matter, One of the most famous examples, Dragonfly 44, located in the Coma cluster, was found to have a mass almost identical to the Milky Way, yet 99.9% of that mass is in the form of dark matter. This is a staggering imbalance. It behaves like a galaxy that formed in an incredibly dark matter-rich environment, but for some reason, the normal matter it should have attracted never quite made it in or was somehow expelled. Other UDGs, however, seem to be devoid of dark matter altogether, which is a paradox that challenges the very foundation of how we believe galaxies must form. How can a large, diffuse structure hold itself together without the gravitational glue of a massive dark matter halo? This stark contradiction within the same class of objects suggests that the label ultra-diffuse galaxy might actually encompass several different cosmic orphans, each with its own unique and tragic history of formation and evolution. Some may be failed giants, born with everything but unable to produce stars, while others may be the scattered, shredded remnants of once normal galaxies, torn apart by tidal forces and now masquerading as pristine, diffuse objects. Unlocking the secrets of these ghostly galaxies is more than an academic exercise. It is a direct test of our understanding of dark matter and galaxy evolution. If they are truly dark matter dominated, they could be ideal laboratories for studying the distribution and properties of dark matter itself, free from the complicating glare of countless stars. If they are devoid of dark matter, they might force a radical revision of our theories, perhaps pointing to alternative models of gravity or exotic formation scenarios. The ongoing hunt involves using the world's most powerful telescopes, like the James Webb Space Telescope and the Keck Observatory, to study the faint globular clusters that often surround these galaxies, as the motion of these clusters can reveal the galaxy's hidden mass. Other teams are using deep spectroscopic observations to trace the subtle movements of the stars within the UDGs themselves, looking for the telltale signs of a massive dark halo or the lack thereof. Each new observation adds a piece to the puzzle, but the full picture of how the cosmic web gives rise to these vast ethereal phantoms remains one of the most captivating and unresolved stories in modern astrophysics. Peering into the depths of space is more than just looking across distances. It is a form of time travel, and the cosmic web serves as our most powerful time machine. Every photon of light from a distant filament has been on an epic journey, sometimes for more than 10 billion years, to finally reach our telescopes. When we observe these ancient threads, we are not seeing them as they are today, but as they were when the universe was a fraction of its current age, our youthful, formative cosmos. This ability to look back through cosmic epochs allows us to watch the web's grand assembly in progress, from its first faint sketches to the magnificent tapestry we see in the nearby universe. Yet, this incredible view has revealed a startling and counterintuitive puzzle. The infant cosmic web appears to have grown up too fast. The filaments we see in the distant, early universe seem more complex, more structured, and more mature than many of our best cosmological models had predicted. It's as if we opened a family photo album expecting to see a toddler, and instead found a picture of a fully formed adolescent. This phenomenon of premature maturity forces us to re-examine the very forces that shaped the early cosmos. For decades, the prevailing model of structure formation was a gradual, hierarchical process. Tiny fluctuations from the Big Bang would slowly, over billions of years, build up through gravitational attraction, first forming small clumps that would then merge into larger and larger structures. The cosmic web, in this view, should have taken its time to emerge, with thin, wispy filaments only becoming prominent and well-defined relatively late in cosmic history. But observations, particularly from powerful instruments like the James Webb Space Telescope, are painting a different picture. They reveal that when the universe was only about 3 billion years old, a mere quarter of its current age filaments of staggering scale and clarity were already in place, channeling gas into burgeoning galaxy clusters. Galaxies were already lining up along these cosmic highways, and the basic architecture of the modern universe was clearly established far earlier than anyone anticipated. The construction of the cosmos, it seems, was a rush job. What cosmic contractor could have worked with such astonishing speed? The prime suspect is once again the invisible hand of dark matter. The specific properties of dark matter particles fundamentally govern how quickly structure can form. The standard model assumes cold dark matter, where particles are slow-moving and readily clump together from the smallest scales upward. But if the observed early web is too developed, it might be a clue that dark matter is even colder or more efficient at clustering than we thought, allowing the cosmic scaffolding to assemble with breathtaking rapidity. Alternatively, other exotic factors in the early universe could have given structure formation a powerful head start. Some theorists speculate that primordial magnetic fields, those faint fossil fields we discussed earlier, could have provided extra pressure and support, accelerating the collapse of gas along the dark matter filaments. Others wonder if a different type of dark matter interaction, or perhaps an early phase of dark energy with a different strength, could have given the nascent web an extra gravitational push. The data is forcing us to consider that the recipe for our universe might have included ingredients or followed instructions that we have not yet fully accounted for in our simulations. This discrepancy between model and observation is more than a minor calibration issue. It's a potential crisis that could reshape our understanding of cosmic evolution. The maturity of the early web has direct consequences for the galaxies it contains. A well-developed filamentary network in the ancient universe means that vast flows of gas were being efficiently channeled into the first galaxies at a very early time. This could explain the existence of surprisingly massive and bright galaxies that JWST has spotted in the very early universe, objects that seem too big to have formed in the time available under our old, slower timelines. The early web provided the infrastructure for rapid galactic growth, turning the primordial cosmos into a more bustling and interconnected metropolis than we ever imagined. The galaxies weren't just forming in isolation. They were being fed by a sophisticated, large-scale supply chain that was operational almost from the very beginning. Resolving this mystery is a primary driving force behind the next generation of astronomical surveys, projects like the Roman Space Telescope and the Vera-C. Rubin Observatory are designed to map the cosmos in unprecedented detail, creating three-dimensional charts of billions of galaxies across vast stretches of space and time. By comparing the web's structure at different cosmic epochs with extreme precision, we can create a stop-motion film of its growth and measure its developmental speed directly. Does the web's complexity increase smoothly and rapidly from the start, or is there an unexplained burst of activity in the first few billion years? The answer will tightly constrain the properties of dark matter and may even point us toward new physics that operated in the universe's high-energy youth. The cosmic web as a time machine does more than just show us the past. It provides a crucial stress test for our entire cosmological paradigm, challenging us to explain why the universe's largest structures were in such a hurry to grow up. But if gravity is the master builder of the cosmic web, tirelessly working to pull matter together into its grand filamentary design, then there is a phantom lurking in the background, an opposing force working just as tirelessly to dissolve the entire structure. This brings us to a mystery that touches the ultimate fate of all things, the subtle but profound influence of dark energy. We often speak of dark energy as the driver of the universe's accelerating expansion, a mysterious repulsive force that acts against gravity. But to truly grasp its role, we need to think of it not as a uniform background effect, but as an active player in the cosmic environment, one whose influence varies dramatically depending on where you are in the vast architecture of the web. Imagine the cosmic web as a magnificent sandcastle on a beach. gravity is the child carefully piling up the wet sand, sculpting towers and connecting walls. Dark energy, then, is the incoming tide. At first, the tide seems distant and irrelevant to the intricate castle. But slowly and inevitably, the water rises, not attacking the castle all at once, but first seeping into the wide, flat areas of the beach, the cosmic voids. Within these vast, empty regions, there is very little matter to provide a counteracting gravitational pull. Here, dark energy operates almost unopposed, causing the voids to expand faster than the universe's average rate. This isn't just space stretching, it's an active, accelerated dilution. The voids grow, and as they do, they push against the delicate walls and filaments of the web, stretching them thinner and farther apart. The sandcastle isn't being smashed by a single wave. Its moat is steadily and relentlessly widening, isolating the central structures and pulling the foundational sand out from under them. The profound mystery, however, is not just that dark energy does this, but precisely how it interacts with the web's complex architecture. The real intrigue lies in the transitional zones, the ghostly outskirts of galaxy clusters and the thinnest, most tenuous stretches of filament far from any node. In these regions, the cosmic tug-of-war between gravity and dark energy is exquisitely balanced. The gravitational pull from the collective mass of the filament is still strong enough to hold its constituent galaxies together locally, preventing them from flying apart. Yet, the dark energy background is relentlessly stretching the space between different filaments and clusters. The effect is a gradual severing of the cosmic web's connectivity. Those long, bridging filaments that link one supercluster to another are under constant tensile stress. Over billions of years, they are not simply stretching, they are being diluted to the point of dissolution. The great cosmic bridges are slowly, silently, turning into isolated threads and then fading into the background expansion. We are witnessing the universe's largest structures being systematically taken apart, not with a bang, but with a silent, phantom-like pull from within the vacuum of space itself. This leads to one of the most revolutionary questions in modern cosmology. Has the strength of dark energy always been constant? Our standard model, which includes dark energy as Einstein's cosmological constant, assumes it is an immutable property of space itself, unchanging over time. But what if that's wrong? The possibility that dark energy's influence could have evolved is a radical one. In the early universe, when matter was denser and gravity's grip was stronger, dark energy's repulsive effect would have been comparatively negligible. It would have been a whisper against gravity's shout, but as the universe expanded and matter diluted, gravity's influence weakened over large distances, allowing dark energy's push to eventually dominate. This is the transition we believe happened about 5 billion years ago, when the expansion of the universe shifted from decelerating to accelerating. Yet, what if dark energy was subtly stronger or weaker in the past than it is today? If it were stronger in the early universe, it would have acted as a form of early dark energy, putting a brake on structure formation. It could have prevented the cosmic web from assembling as quickly and as robustly as it apparently did, which would conflict with the observations of a surprisingly mature early web we discussed earlier. Conversely, if dark energy is growing stronger over time, a scenario embodied in theories of phantom dark energy, then the fate of the cosmic web is far more dramatic and chilling. In such a model, the acceleration wouldn't just continue, it would intensify. The dissolution of the filaments would accelerate. First, the intercluster bridges would vanish. Then, the gravitational bonds holding galaxy clusters themselves together would be overcome, flinging galaxies apart into the void. This could lead to the infamous Big Rip scenario, a truly apocalyptic end where even stars, planets, and ultimately atoms are torn asunder by the uncontrollable expansion of space. While current data favors a constant dark energy, the error bars are still large enough to allow for fascinating and terrifying alternatives. The precise measurement of how the cosmic web has been stretched and pulled apart over the last 10 billion years is our most powerful tool for testing these ideas. By comparing the web's structure at different cosmic epochs, we can effectively measure the past strength of dark energy, searching for any telltale sign that this phantom force is not constant but dynamic. Uncovering such a change would be a revolution on par with the original discovery of the accelerating universe, forcing us to rewrite our understanding of fundamental physics and confront a cosmos whose final act is even more dramatic than we ever imagined. Now, if we were to take a thermometer to these cosmic filaments, the reading we'd get would be anything but consistent, revealing a thermal landscape of astonishing variety that brings us to our 21st mystery, the riddle of filament temperatures. Within these vast thread-like structures, the gas can range from relatively cool clouds just tens of thousands of degrees to the searing million-degree plasma of the WIM. This isn't a smooth gradient. It's a chaotic and patchy distribution of hot and cooler material existing side by side, and the source of this heat, the cosmic furnace that keeps these filaments from being cold, dark rivers, is a puzzle that goes right to the heart of how energy is distributed throughout the universe. Unlocking this thermal history is critical because it dictates how galaxies form, how gas flows, and ultimately where and when new stars can ignite. So what are the possible heat sources for this intergalactic environment? One of the primary suspects is colossal shock waves, the cosmic equivalents of sonic booms, but on a scale that is almost incomprehensible. As the cosmic web assembles under gravity's relentless pull, vast streams of gas don't just merge gently, they slam into each other at speeds of hundreds of kilometers per second. When a massive filament funneling gas toward a growing galaxy cluster collides with another large flow of matter, the resulting collision generates immense shock fronts that ripple through the intergalactic medium. These shocks compress and heat the gas violently, in much the same way that air is heated and compressed in front of a supersonic jet. This process, known as gravitational heating, is a fundamental and pervasive side effect of structure formation itself. The universe, in its ongoing construction, is constantly generating its own background heat through these titanic, slow-motion collisions. But there is another, more focused and violent source of energy, the galaxies themselves. At the heart of most large galaxies sits a supermassive black hole, and when these monsters are actively feeding, they become some of the most powerful engines in the cosmos' active galactic nuclei or quasars. These objects can launch jets of plasma and radiation at near light speeds, stretching for hundreds of thousands of light years far beyond their host galaxies. When these incredibly energetic jets plow into the surrounding filamentary gas, they deposit enormous amounts of energy, creating vast, inflated bubbles of ultra-hot plasma. It's a form of cosmic feedback where the central black hole acts like a colossal boiler, pumping heat directly into the intergalactic environment. This can literally blow bubbles in the WIM and reheat gas that may have started to cool and condense, effectively regulating the growth of the galaxy itself and influencing the entire local region of the web. Similarly, the collective winds from countless supernova explosions within a galaxy can also drive hot material out into the filaments, contributing to this intense and localized heating. The challenge for astronomers is disentangling the exact contribution of each of these heating mechanisms. Is the filament's temperature primarily a result of broad, cosmological shocks from the web's assembly, or is it more heavily influenced by the localized, brilliant flares of activity from galaxies and their black holes? The answer likely lies in a complex combination, but determining the dominant process is key to modeling the cosmic energy budget, a grand accounting of where energy comes from and where it goes in the universe. To investigate this, scientists use powerful X-ray and ultraviolet telescopes to study the spectral fingerprints of the gas. Different elements, when heated to specific temperatures, emit or absorb light at very precise wavelengths. By analyzing this light, astronomers can act as cosmic forensics experts, determining not just the temperature of the gas, but also its density and chemical composition. For instance, the presence of certain highly ionized elements, like oxygen-6 or neon-9, is a clear signature of gas heated to temperatures of hundreds of thousands to millions of degrees, pointing directly to the influence of powerful shock waves or intense radiation fields. Mapping the distribution of these hot and slightly cooler phases within a single filament can reveal the history of energy injection, showing us where a quasar jet has recently pierced through or where two great flows of matter have violently collided. This thermal puzzle is therefore more than just a question of degrees. It is a dynamic record of the violent and energetic processes that have continuously shaped the cosmic web from its birth to the present day. The universe presents us with a breathtaking range of scales, from the unfathomably large filaments of the cosmic web to the bizarre and counterintuitive realm of the impossibly small. Yet, what if these two extremes are not separate worlds but intimately linked? This brings us to a mystery that ventures into deeply speculative and thrilling territory: the potential hidden connection between the cosmic web and the quantum foam, the very fabric of spacetime at its most fundamental level. The idea is as radical as it is elegant, proposing that the largest structures we can observe were seeded by the smallest fluctuations reality allows, creating a bridge between the domains of general relativity and quantum mechanics that have so stubbornly resisted unification. To grasp this, we need to dive into the strange world of quantum mechanics. In our everyday experience, empty space seems like just that, empty, a pure, featureless void. But when we zoom into the Planck scale, distances so tiny they are a billion trillion times smaller than an atom, this picture completely shatters. Here, according to our best theories, spacetime itself is not smooth. It is a seething, turbulent, and probabilistic froth, constantly bubbling with virtual particles that pop in and out of existence, borrowing energy from the vacuum for fleeting moments before annihilating each other. This is the quantum foam, a term coined by physicist John Wheeler to describe this chaotic, fluctuating foundation of everything. It's a realm where the concepts of here and there lose their meaning, and the geometry of spacetime is in a constant state of violent, unpredictable fluctuation. This isn't happening within spacetime. This is spacetime at its most fundamental level. The monumental leap in theory is that this frenetic activity at the smallest possible scale might have been stretched to cosmic proportions, becoming the very blueprint for the universe's large-scale structure. The crucial mechanism for this incredible amplification is cosmic inflation. Recall that in its first fraction of a second, the universe underwent a period of exponential expansion, inflating a subatomic speck of space to a size larger than our entire observable universe. During this violent growth spurt, the microscopic quantum fluctuations, those tiny, random wrinkles in the fabric of spacetime, were not left behind. Instead, they were stretched along with everything else, inflated from the quantum realm to macroscopic sizes. A fluctuation that was once smaller than a proton one moment could, in the next instant, be stretched to the size of a galaxy cluster. These quantum wrinkles, frozen into the fabric of the expanding universe, became the slight over densities and under densities in the primordial soup of matter and energy. They were the initial imperfections, the seeds around which gravity could then work its magic, causing dark matter and ordinary matter to clump, eventually evolving over billions of years into the magnificent cosmic web of filaments and voids we map today. In this breathtaking narrative, every galaxy, every cluster, and every billion light-year-long filament is a fossilized quantum fluctuation, an echo from the frothy dawn of spacetime. This idea is more than just a philosophical curiosity. It is a central prediction of the theory of cosmic inflation, and it has a specific, testable consequence. The quantum fluctuations that are theorized to have been stretched during inflation would not have been perfectly uniform. they would have followed a particular statistical pattern, a specific signature of randomness. When we look at the cosmic microwave background, the afterglow of the Big Bang, and measure the tiny temperature variations that represent those first density seeds, we find that their distribution matches the predicted pattern from inflated quantum fluctuations with stunning accuracy. This agreement is one of the strongest pieces of evidence we have for the inflationary paradigm. It suggests that the specific texture of the cosmic web, the statistical distribution of thick and thin filaments, the sizes of the voids, is not arbitrary. It is a direct, if vastly enlarged, imprint of the quantum mechanical nature of reality at the moment of creation. The universe's largest structures carry the unique fingerprint of its smallest scale physics. Of course, this remains a profoundly speculative frontier. The central challenge is that we currently lack a complete theory of quantum gravity, a framework that seamlessly unites the probabilistic world of quantum mechanics with the geometric description of gravity in Einstein's general relativity. We can describe the quantum foam in a hand-waving way, and we can describe the cosmic web in great detail, but rigorously connecting the two requires a theory that can reliably describe the physics of space-time at those unimaginable energies of the Big Bang. Candidates like string theory or loop quantum gravity attempt to provide this framework, suggesting that space-time may be composed of discrete, fundamental units, tiny loops or vibrating strings, rather than being a smooth, continuous sheet. In such a picture, the cosmic web might be seen as the emergent pattern of a deeper, discrete underlying reality, much like the smooth flow of a river emerges from the chaotic motion of countless individual water molecules. Exploring this connection pushes the limits of our observational capabilities to the extreme. While we have strong evidence that quantum fluctuations were the seeds, directly detecting the specific signature of the quantum foam in the cosmic web is a task for the far future. It would require measurements of such exquisite precision on the properties of the cosmic microwave background or the distribution of galaxies that they could discern between different proposed models of quantum gravity. Future observatories, perhaps measuring the polarization of the cosmic microwave background with even greater fidelity, or mapping the three-dimensional distribution of trillions of galaxies, may one day find a subtle statistical anomaly, a tiny deviation from the simplest inflationary predictions that points toward a specific model of spacetime's quantum structure. For now, the idea stands as one of the most profound and humbling in all of cosmology, a powerful hint that in tracing the grand architecture of the cosmic web, we are not just mapping the universe, but also reading the faint, encoded diary of its quantum origins, a story written in the first moments of time on the smallest possible canvas, then stretched across the entire heavens for us to find. While our own Milky Way galaxy seems like a stable island in the cosmos, it is, in fact, on a colossal journey, moving at a staggering speed of over 2 million kilometers per hour through the universe. But we are not traveling alone. This motion is part of a vast, coordinated flow involving thousands of nearby galaxies, all streaming in the same general direction, as if pulled by some immense, unseen force. For decades, the source of this cosmic current was one of the greatest puzzles in our local universe, centered on a mysterious region we named the Great Attractor. This invisible gravitational behemoth, located about 250 million light-years away in the direction of the constellation Centaurus, was exerting a pull so powerful it was bending the paths of entire galaxies, including our own. The mystery was compounded by a simple observational problem. Our view of this region from the Milky Way is heavily obscured by the dense gas and dust of our own galaxy's central plane, a zone astronomers call the zone of avoidance. It was like trying to identify the source of a powerful river's current while standing in a dense, obscuring fog. The initial discovery forced a profound realization. The Great Attractor could not be a single, isolated supercluster. The sheer amount of mass required to generate such a vast flow was far greater than anything visible in that part of the sky. This led astronomers to a revolutionary idea: the Great Attractor is not a solitary destination, but rather a signpost, a single massive node within the much larger, underlying river system of the cosmic web. Our motion is not a simple beeline toward one point. It is a complex journey guided by the gravitational landscape of the local filamentary structure. We are flowing along a cosmic superhighway with a gentle but relentless pull of the filament's dark matter backbone guiding us toward its most massive intersections. The Great Attractor itself is now understood to be a massive confluence, the Norma cluster, sitting at the heart of a larger superstructure called the Laniakea supercluster, of which our Milky Way is a distant outlying member. Laniakea, which means immense heaven in Hawaiian, is a web-like filamentary network of over 100,000 galaxies, all gravitationally bound and flowing toward a common center of mass. The Great Attractor is a major gravitational pit along that journey, but it is not the end of the line. In fact, the story continues far beyond our local supercluster. The galactic flow we are part of does not stop at the Great Attractor. Our entire Laniakea supercluster, along with other nearby superclusters, appears to be part of an even larger and more powerful river, streaming toward an unimaginably massive concentration of mass that has been dubbed the Shapley Attractor or the Shapley supercluster. Located over 600 million light-years away, Shapley is the most massive known concentration of matter in our local universe, a colossal knot where several immense filaments of the cosmic web intersect. The gravitational pull from this distant, titanic structure is so immense that it is influencing the motion of galaxies across a volume of space nearly 1 billion light-years wide. Our journey, therefore, is a multi-layered one. We are moving within our local filament toward the Great Attractor, while simultaneously our entire local supercluster is being pulled toward the far more distant and massive Shapley supercluster. It is a cosmic hierarchy of flows, with smaller rivers feeding into larger ones, all dictated by the invisible topography of dark matter. This revelation fundamentally changes our understanding of these cosmic anomalies. There is no single Great Attractor in the sense of a unique, mysterious object. Instead, these attractors are simply the visible manifestations of the cosmic web's most dense nodes. They are the bustling, gravitational downtowns of the universe, and the filaments are the freeways that channel traffic toward them. The mystery has shifted from what is pulling us to what is the full extent of this web, and what other unimaginably massive concentrations of matter lie hidden behind the veil of our own galaxy. The true power of the Great Attractor saga is that it revealed our place within a dynamic, flowing cosmos. We are not static observers, we are participants in a grand, gravitational migration, riding the currents of the largest structure in existence, pulled by shadows in the deep that we are only just beginning to map. This grand architecture, with its intricate patterns of filaments and voids, might hold more than just the secret to the universe's structure. It could be safeguarding the oldest record of all, a cosmic memory etched into the very fabric of space. The specific twists, turns, and connections of the web are not random. They are a frozen echo, a direct imprint of the universe's earliest possible moments. Just as a towering ancient tree contains within its rings a perfect record of the climatic conditions of every year it lived through, the cosmic web holds within its geometry a permanent memory of the initial conditions from which it was born. This makes the entire observable universe not just a collection of objects, but the ultimate archaeological site, a billion light-year-wide fossil that, if we can learn to read it, tells the story of creation itself. The concept of a cosmic memory hinges on a principle in physics known as determinism. In its simplest terms, the idea is that the state of the universe at any given moment is a direct and inevitable consequence of its state in the previous moment, a chain of cause and effect stretching all the way back to the beginning. The quantum fluctuations that were inflated during the universe's first fraction of a second set the initial conditions, the very first entry in the cosmic ledger. From that point forward, the laws of physics, primarily the relentless force of gravity acting on dark matter, took over and executed a complex but deterministic calculation that has been running for 13.8 billion years. The outcome of that ongoing calculation is the specific pattern we see today, the precise length of a particular filament, the specific diameter of a void, the exact angle at which three filaments intersect to form a massive cluster. Every detail is a logical, if immensely complex, consequence of those first moments. The web doesn't just have a history, it is that history written in a language of gravity and matter. Think of it like a vast and intricate game of dominoes. At the start of the game, someone sets up the first domino in a specific, slightly wobbly position. They then set off a chain reaction. The precise way that first domino falls determines the path of the entire spectacular cascade that follows. The final pattern of thousands of fallen dominoes is a direct, frozen record of that initial tiny wobble. In our cosmic analogy, the initial quantum fluctuation is that first domino's position, and the cosmic web is the magnificent, sprawling final pattern. The great filaments are not merely structures, they are the final frame of a movie that began at the Big Bang, and by studying this single, frozen frame with enough precision, we can theoretically rewind the film and deduce what the very first frames must have looked like. This is where the cosmic web transforms from an object of study into a tool for discovery. The most critical information locked within this cosmic memory concerns the nature of cosmic inflation. The statistical properties of the initial quantum fluctuations, their strength, their distribution across different size scales, are a direct signature of the physics that drove inflation. Different models of inflation, which propose different types of inflationary fields or energies, predict subtly different statistical patterns for these primordial seeds. By meticulously mapping the cosmic web in 3 dimensions, measuring the thickness of filaments, the distribution of their lengths, the sizes and shapes of voids, and comparing this map to the predictions of supercomputer simulations, we are effectively conducting a forensic analysis of the inflationary epoch. We are asking the web, were the initial fluctuations perfectly random, or did they favor certain scales? Was the process perfectly smooth, or were there phases and transitions? The web structure holds the answers, acting as a colossal experimental result that can confirm or rule out our most fundamental theories about the universe's birth. Unlocking this memory, however, is a task of almost unimaginable complexity. The challenge is that the pristine initial conditions have been processed and evolved over billions of years. Gravity is not a perfect archivist, it is a dynamic and sometimes messy sculptor. The gentle initial fluctuations have been wildly amplified, and later astrophysical processes, supernova explosions, galactic winds, the furious energy from quasars have injected their own noise into the system, like later scribbles overwriting parts of an ancient manuscript. The cosmic web's memory is not a perfect, unaltered recording. It is a palimpsest where the original text is still there, but it has been written over by the subsequent tumultuous history of the universe. The great task for cosmologists is to separate the signal, the primordial blueprint, from the noise of later astrophysical events. This requires incredibly sophisticated simulations and statistical tools that can model the entire history of the universe, from the quantum foam to the present-day web, and then compare that virtual universe to our painstakingly collected observations. Every new, vast galaxy survey, like those from the Dark Energy Spectroscopic Instrument or the future Roman Space Telescope, adds more data points to this cosmic census, sharpening the image and allowing us to read the memory with ever greater clarity. The ultimate goal is to see through the later chaos and glimpse the pristine order of the beginning, to hear the faint, original note that set the entire cosmic symphony into motion. And that brings us to the final, and perhaps most grounding, mystery in our journey, the profound challenge of simply seeing the cosmic web at all. Confronting this structure means pushing against the absolute limits of observation, a battle fought with engineering genius, computational power, and a fair amount of philosophical humility. The sheer scale and faintness of the web present a problem so immense that every step forward in mapping it is a triumph of human ingenuity over cosmic subtlety. This isn't like spotting a bright planet or a nearby galaxy. It's an exercise in trying to photograph a ghost using a camera that is, itself, trapped inside the haunted house. The first and most fundamental obstacle is the sheer dimness of the filaments. Their primary component, the warm-hot intergalactic medium, is a gas so thin that a single cubic meter of it might contain only a few particles, a vacuum far more perfect than anything we can create on Earth. This tenuous material doesn't glow with the vibrant light of stars. It emits only a faint whisper of energy, primarily in the high-energy X-ray part of the spectrum, or by subtly absorbing the light of distant, brilliant beacons known as quasars. Catching this whisper requires telescopes of staggering sensitivity, instruments that must stare at a single patch of seemingly empty sky for days, even weeks, to collect enough individual photons to build up a statistical picture. It's a painstaking process akin to trying to hear a single, quiet conversation from miles away by using a colossal listening dish to gather every faint sound wave over an entire month, then piecing the conversation together from fragments. Our great X-ray observatories like Chandra and XMM Newton have achieved this for the densest knots of the web near galaxy clusters, but tracing the faint, ethereal gas along the vast, lonely stretches between clusters remains at the very edge of our capabilities. The next generation of X-ray telescopes, like the proposed Athena mission, are being designed with this specific goal in mind, their huge collecting areas acting as colossal light buckets to finally illuminate these dark, flowing rivers of the cosmos. But observing the gas is only one piece of the puzzle. The overwhelming majority of the filament's mass is the invisible dark matter, which emits no light at all. To map this hidden skeleton, astronomers must become cosmic cartographers of the unseen, using the motions of galaxies as their guide. This relies on a powerful technique involving sophisticated computer algorithms that analyze the three-dimensional positions of millions of galaxies. The process begins with massive sky surveys that painstakingly measure the distance to each galaxy, often by obtaining its spectrum and measuring its redshift. This creates a colossal three-dimensional point cloud of the universe. The algorithms then step in, searching for statistical patterns in this cloud. They look for galaxies that are closer together than a random distribution would predict, identifying the long, tendril-like chains that trace out the underlying dark matter filaments. It's a monumental game of connect the dots, but where the dots are cities separated by thousands of light years, and the lines connecting them are drawn by the invisible hand of gravity. This method has been spectacularly successful, revealing the web in stunning detail, but it is entirely dependent on the scale and precision of the galaxy survey. Any gaps or inaccuracies in the map can lead to filaments being missed or misinterpreted, leaving holes in our understanding of the cosmic skeleton. Perhaps the most mind-bending challenge of all lies in the fact that we are inside the structure we are trying to map. We can't simply fly outside the universe to take a picture of the whole web. Our perspective is inherently limited and local. This creates a phenomenon known as the finger of God effect in our maps, where the gravitational pull of a massive nearby cluster, like the Virgo cluster, can distort the apparent positions of galaxies behind it, stretching their distribution into a long, pointed shape that mimics a filament but is really just a measurement artifact. Disentangling these local distortions from the true, large-scale structure of the universe requires incredibly complex models of galactic motions and gravitational fields. Furthermore, the expansion of the universe itself sets a hard limit on what we can ever see. there is a cosmic horizon, a point beyond which light has not had enough time to reach us since the Big Bang. The most distant, and therefore earliest, filaments are forever beyond our direct view, their light stretched into oblivion or lost in the primordial glow of the cosmic microwave background. We are like deep-sea explorers in a vast, dark ocean, able to map the terrain immediately around our submersible with sonar, but with the distant abyss forever cloaked in an impenetrable gloom. Ultimately, the quest to map the cosmic web is more than a technical endeavor. It is a fundamental test of our ability to comprehend reality. Each new map, each faint detection of intergalactic gas, is a testament to our species' relentless curiosity. We are building ever larger telescopes on remote mountaintops and launching them into the quiet of space. We are writing ever more clever algorithms to sift meaning from petabytes of data. We are, in a very real sense, constructing a pair of glasses that allows us to see the invisible architecture of our universe. The cosmic web does not give up its secrets easily, but with every technological leap and every new insight, we pull back another layer of the cosmic veil, revealing a little more of the magnificent, threadbare tapestry we call home. Our journey through these 25 cosmic riddles has taken us from the quantum tremors of the Big Bang to the phantom flows of dark energy, all woven together by the universe's grandest feature. We have seen how dark matter's invisible hand sketched the blueprint, how filaments act as both cradles for infant galaxies and conveyor belts guiding them to their fate, and how these structures hold the missing pages of the universe's diary, from its fiery first moments to its cold, distant future. The cosmic web is far more than a beautiful pattern. It is the central character in the story of our cosmos, the stage upon which every galaxy, star, and planet plays its part. Its filaments are the connective tissue of everything, the great rivers of matter and energy that dictate the rhythm of cosmic evolution. To study them is to ask the most fundamental questions we can pose. Where did we come from? What is the universe made of? And where is it all going? Unraveling these intertwined mysteries is not a passive academic exercise. It is an active human endeavor that defines the frontier of our understanding. Every faint X-ray whisper we detect from the warm, hot intergalactic medium, every subtle distortion in starlight that reveals a hidden knot of dark matter, every new map of galactic flow, each one is a crucial piece of the puzzle. The answers we seek are not just about filling textbooks, they are about comprehending the very laws of physics that govern reality, from the smallest quantum grain of space-time to the vast, accelerating expanse of the cosmos. The cosmic web is our ultimate laboratory, a natural experiment operating on a scale we can never hope to replicate, offering clues to the nature of dark matter, the identity of dark energy, and the validity of our most cherished theories. Solving one of these puzzles often reveals two more, reminding us that the universe is far stranger, more complex, and more wonderful than we ever imagined. So the next time you find yourself under a clear night sky, far from the glow of city lights, take a moment to truly look up. See the stars, the band of the Milky Way, the faint smudge of the Andromeda galaxy. But then, let your mind's eye push further. See beyond those nearby streetlights of our cosmic city. Envision the magnificent, invisible architecture that connects them all, the immense, delicate filaments stretching across the unimaginable void, a web of gravity and mystery in which our entire galaxy is but a single, shimmering thread. Remember that you are not just looking out at the universe, you are living inside its largest structure. The atoms that make you, the planet you stand on, the star that gives you life, all were forged in the hearts of long-dead stars and delivered to this quiet spiral arm along these ancient, flowing rivers of the cosmic web. You are a part of this story, a conscious expression of the universe becoming aware of itself. The greatest mystery of all may be that we are here to ask these questions, to gaze in wonder at the tapestry, and to feel the profound connection to a cosmos that is at once overwhelmingly vast and intimately our own.